By the second half of the morning will be polar BGC stuff, so polar BGC and ecosystem talks. So for online participants, there's a Slido if you want to ask questions. So go ahead and insert questions in the Slido. What else? Each speaker has 15 minutes, but that includes questions. I'll be keeping time, and then when your time is about 12 or 13 minutes in, I'll stand up just so you know your time is almost done. And yeah, I think that'll do it. Okay, so we'll have our first speaker, who is Abby Swan, one of the other BGC co-chairs.
All right. See what my slides look like. Welcome, everybody. I'm Abby Swan. I'm one of the Biogeochemistry Working Group co-chairs, along with Kristen and Gretchen Keppel-Alex. I'm going to talk this morning giving an update on some of what's happening with carbon over land in the flat 10 MIP experiments. I'll explain what those are. Our first 3 talks are actually going to talk about these experiments, so hopefully this will give you an introduction to thinking about what's going on in these emissions-driven runs. And I want to acknowledge co-authors, including Charlie here in the room, Ben Sanderson. So I'll start by reminding folks in this room that emissions-driven simulations using global climate models or Earth system models show a big spread in atmospheric CO2. But in CMIP6, we only have a limited number of models that did these emissions-driven simulations. We're hoping that there will be more in CMIP7. It's a request of the experimental design to have more emissions-driven simulations. So these are simulations where emissions are specified rather than CO2 concentrations, and that results in a spread of atmospheric CO2 in any particular scenario. For this example, for I think SSP 585, it's got a 250 parts per million spread in 2100. This spread is largely, but not entirely, due to differences in land fluxes of carbon, which is not at all to say that ocean carbon cycling isn't important, but the uncertainty is really huge on land. So we've got, these are squished to be on the same scale. This is the cumulative land flux from the C4 MIP and CMIP6, and this is the cumulative ocean flux. And so there's just a lot of uncertainty in land processes that lead to large uncertainties in land carbon sinks. And those changes in land carbon sinks as well as ocean carbon sinks lead to changes in atmospheric CO2 concentrations, which lead to differences in temperature. So this is the same CO2 concentration spread that we saw 2 slides ago, and that leads to these blue simulations showing you a range of different temperatures from those simulations. So this new experimental design for CMIP7 is called the flat 10 set of experiments, and we've run a small model intercomparison using CMIP6 era models, and that's what we'll be looking at today. And it's part of the fast track for CMIP7, so there should be a lot more of this experimental protocol for CMIP7. The way it works is that it's specified through emissions of carbon dioxide. Emissions are flat at 10 petagrams carbon per year for 100 years, so that's cumulative emissions of 1,000 petagrams. Then there's 3 different experiments. There's a continuation of that one in gray. Sorry, this is a little hard to use. There's the the orange one that drops to 0 emissions and then stays at 0 emissions. And then this blue one, which will ramp down to -10 till it and then go for 100 years till it gets to cumulative emissions that are 0. So it basically removes, through some unknown, unspecified process, it removes all of the carbon that was put in through emissions. And so the cumulative emissions look like the plot on the right, where you have the orange line showing that cumulative emissions stay flat at 1,000 petagrams per year for the 0 emissions run, and the blue one where it's ramping down, you have cumulative emissions peak and then decline back and eventually end up back at 0. So there's a paper out now led by Ben Sanderson in GMD that describes the sort of high-level global scale responses in these simulations. So broadly for land, what we find is that the land carbon sink increases while emissions are increasing. So this is CO2 fertilization, higher productivity with warming, et cetera. And this is the emissions phase. So where there's an emission of 10 petagrams carbon per year. There's a relatively large spread. It doesn't look huge on this plot, but you can see we've got more than 100 petagrams carbon spread across the different models. Then we go into a phase of zero emissions, where the emissions are staying flat. We can see that the spread remains large. Models are relatively flat. There's a little bit of decline in some of them in the land carbon sink. And then in the simulation where the emissions are removed, you can see that carbon in the land carbon sink peaks at some time and then declines. And those peak land sinks happen at different times. So I wanted to introduce two other metrics that we're interested in that I think will also come up in these first three talks. We have some aspects of the climate system which we think depend on both the physical climate system as well as the carbon cycle response. And there's work ongoing and to understand how the carbon cycle response is influencing these climate metrics. The first one is the transient climate response to emissions, or the TCRE. Emissions of carbon dioxide specifically. So this plot from the IPCC shows cumulative CO2 emissions on the x-axis and global mean warming response on the y-axis. And you can see that it's this relatively linear response across a lot of different scenarios in different colors, as well as during the historical period. So we can sort of envision the flat 10 experiment as tracing out this emissions period where we have constant emissions and then going to zero emissions. The second metric is called the zero emissions commitment, and it is the amount of temperature change you get after reaching zero emissions. So imagine if we stopped emitting right here, that we would then have some amount of either warming or cooling or potentially flat temperatures that follow the cessation of emissions. So cumulative emissions are no longer rising, but there could be slight changes in temperature due to the rates of ocean heat uptake and like global carbon sink. So what do these look like in the flat 10 experiments? Here's different models in different colors looking at that increasing emissions period at the transient climate response to emissions. You can see they do have different TCREs across the different models. And here is the zero emissions commitments. Again, there's sort of maybe bulk of them a little bit less than zero, depending on how far out you go from zero emissions. But there's a range of these. And they have very broadly about the same range as they did in the ZECMIP experiments from CMIP6. Okay, so this is looking sort of at the global scale response. We're going to dig in a little bit more regionally to try to understand what it is about land that's changing that might be influencing carbon. So this is just looking at the total carbon on land and how that progresses over the emissions time period. And I haven't normalized anything here, so you can see that there's big differences in the initial carbon stocks on land. So this is starting out just globally averaged. There's a really big spread in sort of how much carbon these different models have on land. And there's an increase in this over the emissions time period, just like we saw in the other figure. If we want to dig in a little bit more spatially, this is now looking at a zonal profile. So for CESM2 to start with, we have the equator here in the middle, North Pole at the top, South Pole at the bottom, and we're plotting the total carbon is the top orange, the top solid line. The solid shaded area is soil carbon, and the dashed lighter shaded area is vegetation carbon. If we see a blank area, that's litter carbon. And this is in petagrams carbon, so including the area. We've already accounted for the area here. This is the total carbon stocks. And you can see for CESM that it's got a pretty large soil carbon stocks at high latitudes, large vegetation carbon stocks in lower latitudes. So I'm going to shrink that one down, and now I'm going to show you a bunch of the different models just so you can see approximately how they compare with one another in terms of the distribution of where their carbon is. They're going to be on different x-axis scales. So I haven't, so you'll note this one goes to about 60, and they are different here, which you'll see why. So we'll put them all up here, and you can see that a lot of them are sort of in the ballpark range of CESM's total carbon, but then we've got NOR-ESM down here, which has really, really, really large high latitude carbon stocks. And so the scales are not all equal. We also have a few models that have a little bit less carbon on land. So we can see that they share some sort of broad characteristics of their distribution, generally a lot of soil carbon at high latitudes, higher carbon stocks in the tropics. This is just to give you the initial sense of what they look like. But we want to understand how this is changing under different emissions. And so here's that plot we saw before of the change over the emissions period. Now I'm going to bring in the soil carbon and the vegetation carbon, so we can see the carbon gain during the emission phase is mostly in vegetation. Presumably this is a lot due to CO2 fertilization, although I need to look into that more carefully. So we have, sort of higher carbon stocks in soils, but they're not changing as rapidly as the vegetation carbon. If we look now during the zero emissions period, so you can think of this as continuing the time series into zero emissions, you can see that relative to the initial stocks, the changes are relatively flat. If we're losing carbon, it's mostly in the vegetation, but they're small declines after we go to zero emissions. And if we think instead about the experiment where we're declining emissions, so if you think about this, the emissions are being removed, so CO2 in the atmosphere should be going down, temperatures should be getting cooler, CO2 fertilization might be going away. We can see that we have big declines in vegetation carbon associated with this as we go back to cumulative zero emissions. And that leads to declines in the total global carbon stocks as well. So I have lots of questions, and I haven't answered pretty much any of them yet, but I'll show you what I'm thinking about with them so far. So I want to understand not just that the models are different, but why they're different, what's determining this land sink size, what's causing variations in the location of the land sink, does this location and or size of sink determine aspects of TCRE or ZEC. So I'll show you just what I've been working on with this so far. I've been trying to think about how different factors might influence these. So this is looking at the initial carbon stocks, looking at the initial carbon stocks on the x-axis here for a given model. And then the total carbon gained during the emissions phase. So, does your initial carbon stock size determine your response to change? And I guess we could say maybe, but then we could say, well, maybe this red one down here, if we leave that one out, I don't know. These are not very impressive correlations. So then I could say, okay, now we've moved that plot up here to the left here. That's the global carbon. Maybe we could look at it by latitude band. And so there maybe is a little bit more correspondence in tropical latitudes and mid-latitudes between initial carbon stocks and carbon response. But I still wouldn't find this to be overwhelmingly impressive evidence. So returning back to these zonal profiles, which I know are a lot of information, but I think also we can sort of get some visual feedback from them. We can see the carbon gain during the emissions phase is mostly in vegetation in most of the models. That makes sense that if there's large CO2 fertilization, the first thing to grow might be the vegetation. But we do have models that are all soil for probably structural reasons here. They don't think they have changes in leaf area. But then we have other models where there's no soil response at all, and it's all vegetation carbon. Whereas then you sort of have the rest of the models which have a response, some in the soil as well as in the vegetation. So this is additional carbon. Okay, I'm running out of time here. This is to look at the carbon gain or change during zero emissions, and you can see that there is carbon gain at mid and high latitude in most models, but not all models. So I'd like to understand more about that. And I'm going to show you the next slide, which looks a lot like this one, but is actually different. So this is the carbon gain while we had zero, or change while we have zero emissions. But now if we go back to cumulative zero emissions, how does it look different? And it changed slightly, but the sort of thing that I've noticed on this one, which is interesting, is that many of the models lose carbon in the tropics after all the anthropogenic CO2 is removed. So some of them are keeping some of their high latitude carbon, but not mid and high latitude, not all, but the tropical carbon is being lost in many models. Okay, so does TCRE relate to carbon sink? No, not really. What about ZEC? Nope, not that one either. So I don't really have any answers for those, but we do know that there's a large spread in TCRE in an old perturbed parameter ensemble from the Hadley Center, and so it's larger even than the spread across the flat 10 MIP models, and so I'm really interested in running multiple CESM ensemble members to see how large a spread we can get within CESM if we change aspects of land carbon cycling. So I'm working on that now if anyone wants to help me figure out how to get the spin up to work. Okay, so models are different. I'd like to understand why they're different, but I'm still working on these questions and haven't really solved them yet. If you want to sign up for the mailing list for our working group here, the link is here if anybody's not on it. So thank you. Questions? Anyone? One question?
Have you looked at, when you're trying to look at the accumulation versus total stock size, have you looked just at the vegetation carbon separate? As being maybe because soil
Yes,
carbon is
I
so
have.
wild.
It doesn't help either. Yeah, I've made I didn't want to subject you to all of the scatter plots, but basically nothing I've looked at so far has helped. But I think I need a little bit more time to actually sit and think about it. But if other people have other ideas of like what factors to look at, I'll definitely try to do some analysis on the fertilization response and see if that helps explain the emissions phase. But I think understanding the sink response during zero emissions would be useful as well, which maybe Charlie's going to tell us about in the next talk. So, okay, thanks everyone.
Thanks, Abby. Yeah, for the intro, and I'm also going to talk about flat 10 MIP simulations. Away from my slide. Here we go. Yeah, okay, so this one's, what I want to talk about are the timescales and the symmetry of the land and ocean carbon responses to prior CO2 emissions. And this is also using the flat 10 stuff, and we've got contributions from lots of people, many institutions around the world. Okay, so I want to start off with this figure from the most recent Global Carbon Project. So, until about a decade ago, CO2 emissions were rising exponentially. And the problem with when you're on an exponential is you can't, it's very hard to tell if something's proportional to the instantaneous emissions at sort of one extreme of the timescale spectrum, or if they're proportional to cumulative emissions at the other extreme of the timescale spectrum, because the two things are proportional to each other for as long as you're on an exponential. And so, so this is showing the annual emissions, and this is the cumulative carbon emissions, right? And so we know that the land and ocean sinks are responding to emissions, but you can't, as long as you're on the exponential, you get very little information about the actual time scale over which the land and ocean is responding to these prior emissions because of this proportionality. About a decade ago, that story changed, right? Emissions have basically, been flat for a decade, and so we're now actually off the exponential. Hopefully we stay off that exponential, and hopefully we start going the other direction at some point soon. And so the question is once you get off this, then these timescales start to matter a lot, and we start to, it starts to be important how rapidly the land and ocean sinks are responding to these prior emissions. Are they responding to the total cumulative emissions that have occurred before them, or is it some timescale, or is it just very instantaneous? And so you can just generalize this as thinking there's some relaxation timescale or memory timescale over which the land and ocean is sinking, and we don't know, to observationally what those are. At the other extreme, if you do something really crazy, like you reverse emissions in this experiment that we did a few years ago, it's sort of one of the precursor experiments to what's gone into 510 MIP. You start with positive emissions, you start with something like exponential, but then once you get off the exponential, and if you do something really crazy and reverse them, what you see is that the land and ocean sinks are responding basically to how you do emissions, right? If you switch emissions from positive to negative, the land and ocean carbon sinks also switch from positive to negative, and they do so pretty quickly, with about a decade or so of lag. And so basically, there's this relatively rapid response of the land and ocean sinks. But it's difficult in this to really sort of get all of the kind of information you might want about about the timescales and symmetry of that. And so Abby already gave an intro to flat 10 MIP. So yeah, there's these three experiments: one flat 10, one flat 10 ZEC, and this other one flat 10 CDR. So what I want to do is ask if we try and fit like a sync response to prior emissions using this nice step functions that you get in flat 10 ZEC experiment. Can you then use that as basically as a null hypothesis to ask, if the response to negative emissions, is there anything special about that, or if it's just showing the same kind of spectral response to prior emissions that you get under the sort of positive and zero emissions. And yeah, so I already showed some of this again, but I just want to go over. So this is atmospheric CO2 in each of these experiments, right? So under flat 10. CO2 starts decreasing. You can see there's actually a bit of a positive curvature in a lot of the models for flat 10 because of the weakening land and ocean sinks with continued emissions. Under flat 10 ZEC, once you stop emitting, the CO2 starts to drop somewhat, and then in flat 10 CDR, it reverses and ends up actually lower than during the pre-industrial. And then this is the land sink, which again, you can see this kind of weakening under flat 10, which I don't want to get into here, but it's an interesting feature. And the flat 10 ZEC, Abby showed this bunch, it basically continues for a little while and then it basically stops, right? These are the cumulative sinks. So stopping the cumulative sink means the instantaneous sinks is stopping, and then or going to zero, and then in the flat 10 CDR, things reverse. And then similarly, the ocean, right? So the ocean, in the flat 10, it actually stays fairly proportional to emissions. In the flat 10 ZEC, what you see is it flattens off, but it doesn't flatten off as much as the land, right? The ocean sinks continue even after zero emissions. And in the flat 10 CDR, you get sort of a shift a bit. The spread's a lot narrower, as Abby was showing, and also the sinks continue for a bit longer. And it doesn't actually reverse the way it does in land. Okay, so what I want to do here is basically fit this memory, try and determine what the memory is, right? What's the time scale over which the land sinks are responding to these prior emissions? So you can basically just kind of, fit an exponential decay function of the land sink as a function of prior emissions. And if you do that, on the land, you basically only need a single memory time scale. And it's relatively short, right? On the scale of like 1 to 10 years. Some of the models are faster than others. So this is sort of, the black line is this fitting this function to each of the models. And I should say, you see a lot of other interesting differences between the models. The basic stuff like just the strength of the land sink, interannual variability is just completely different across all the models. Some of them, UVic is a sort of intermediate complexity model, so that basically doesn't have an interannual variability. GFDL has huge interannual variability, right? You can see that there's a lot of these differences. But the key thing is that you can see this kind of, this response time scale over which the land sink is responding to prior emissions is it's a decadal time scale for most of these models. In the ocean, what you see is you basically can't fit a single time scale for the ocean, which I think we kind of know this, but it's a useful exercise to go through. If you try and fit a single time scale, which is what these dashed lines are, you basically can't do it. Whereas a two time scale model, where one is partially responding on a less than decadal time scale and partially responding on a slow component, on a centennial time scale, actually fits these responses quite well. And so you can start to tease apart what are these time scales on the ocean model. Now, again, one of the goals here is to ask, well, can we use these kinds of functions that we fit under flat 10 ZEC and use that as a null hypothesis to see if there's anything interesting going on under this flat 10 CDR, or if it's just the response to prior emissions, but with a different emissions pathway. And the answer is that, actually you do see, in a lot of the models, you do see some interesting dynamics, particularly late in this scenario when you've gone to very strong negative emissions, that you get this divergence between what the model's doing and what you would, the black lines here, I should say, are a prediction of using that sort of exponential decay model, basic impulse response, over, that's, forced by this forcing function. And so you do see a divergence in several of the models late in the simulation. There is something fundamentally different going on under negative emissions than just the same memory timescale applied to a different function. But not all the models, right? Some of the models, it actually works quite well, even under negative emissions, right? Like you can see in this UK CESM and many other models. So it's not, so I think there's and we don't know exactly why these differences emerge, and this is kind of one of the things we want to look into. Likewise in the ocean, Some of the models actually show stronger ocean carbon sinks in response, sources in response to this reversal in emissions than you would get by just using this kind of null hypothesis informed only by the flat 10 and flat 10 ZEC experiments. And so there does seem to be something qualitatively different that happens under negative emissions than just the response to zero emissions. So just to conclude, we can use these flat 10 experiments to probe some of these timescales in response to the memory, the timescale of memory for carbon cycle emissions. Land and ocean carbon sinks respond very quickly, on a sort of decadal timescale or shorter even. But the ocean also then has this longer centennial timescale memory. The symmetry of this carbon response is positive negative is model dependent. Some of them are very symmetric. You basically, like the null hypothesis from the ZEC experiment actually explains the CDR pretty well. Others show that there's a stronger source transition after you go to negative emissions than you would predict. And we should understand what that is. And this is sort of one part of the story for what governs ZEC and these related path dependency metrics that Abby was talking about. Of this relationship between global tourist temperature and cumulative emissions. And I think more generally, hopefully emissions start to actually decline and we can actually start to probe this in the real world. But until that point, it's useful to ask, what would we expect to see if and when emissions actually do start to decline using these experiments? So I'll stop there.
All right, I have a question. So you're looking at these timescales and you've diagnosed the timescales for land and some timescales for ocean. And we also know that simple climate models use timescales in a sort of impulse response function kind of way. Do you think these timescales can be used that way, or do we need different experiments to quantify the timescales that you would put into, say, a fair impulse response model?
Well, I think the simple climate model, they're asserting these timescales, right? And we don't actually know whether or not so I think, part of the goal here is to ask, to extract what are the timescales, and B, how general are these timescales, right? Part of the reason for setting this up is kind of like does this null hypothesis explain the responses? We don't know, right? In the simple climate, if you assert it to be the case, then obviously it would be the case. But the Earth, ESMs are our best estimate to actually ask whether or not that these timescales are general. So yeah, that's kind of the idea.
It's really nice talk. I guess my question is, so for the discrepancy between the impulse response fitting versus what the model's doing, how much do you think is the carbon climate feedback versus some other dynamics that we don't understand?
Yeah, I think that's a really good question, and that's why it would be cool to do a BGC coupled version of this, right? You see, I think this kind of thing is like the likely culprit here for this kind of loss of the land sink with continued warming or continued emissions are these carbon climate feedbacks. I think that would be the hypothesis. Is the carbon climate feedbacks show up in this, over here, I have no idea. Maybe it's there. Maybe, I think we need to do the BGC coupled experiment to actually answer that question, because I don't know. I don't think we know a priori what the cause of these things are. Maybe maybe in the kind of decomposition into pools and latitude structure from like the Abby was showing, you can figure out some of this stuff. But I think
for the flat 10 one, it could be right that it's curving up from the carbon climate feedback.
Yeah. Yeah, you see less of it in the ocean than on the land. I think right. You see those lines are fairly straight. In the land, you see a really strong growth, but it could just be also that CO2 fertilization saturates for different plant, for plants, and this gets into all the structural uncertainty. Right? If you put in TBU limitation, then you're basically imposing a point at which CO2 starts to saturate. And anyway, so it could just be those kinds of things, but we don't actually know until we've done the experiments.
Yeah, remote. Anastasia Romano.
Yes, hi. I'd like to start sharing. Why do I have disabled screen share. You need to stop sharing, I think.
We're working on it in the room here.
Mm-hmm. Thank you.
Should be good to go. Okay, it should be good to go. Can you try again?
No, I still cannot start screen share while the other participant is sharing.
Would you like to try to, oh, thumbs up from the back of the room?
Okay, now I can.
Okay, great.
Thank you. Okay, great. So here we are. Okay, so hi everyone. This is Anastasia Romano, and I'm here together with my colleague Paul Lerner. We are research scientists at the NASA Goddard Institute in New York and Columbia University. This is a shout out to my institute, the NASA Goddard Institute, which was recently displaced from its office space the last 60 years. But we are continuing in no man's land. We are currently sitting here at the Columbia University, but hopefully we will find a permanent space soon. This work is with collaborators Hannah Liddy, John Mikus, and Gavin Schmidt. And of course, it represents work that is being done in the entire Model E team at GIS, building the climate model, the Earth system model. And I will also discuss some of the flat 10 experiments that you heard about before and results and how the AMOC is actually playing a role in setting the ZEC and also conditions for reversibility. The research questions that we are addressing in this work, which is work in progress, is where does the heat and carbon enter, exit, or are stored in the ocean? What is the relative role of the ocean heat and carbon uptake in the global mean surface temperature change? How does the ocean heat and carbon uptake vary with the overturning circulation in different models? And what is the ocean's role in climate reversibility? And we are looking that under positive, zero, and negative emissions. First, I want to discuss a set of experiments that we have done. These are following the ZECMIP protocol, but expanding it across different cumulative emissions levels. So we have the 1% emissions driven run, which is shown here as the the gray line, emissions-driven run, and we stop emissions at different levels of cumulative emissions: 800, 1,000 petagrams, 12, 15, 1,700, and 2,000 petagrams carbon. And you can see the atmospheric CO2 concentration response on the panel A, the global mean surface temperature change from the pre-industrial in panel B, and in panel C, the ZEC, the zero emissions commitment, the temperature from the point of zero emissions. And you can see that in the lower levels, the temperatures in the system will stabilize very quickly. In the higher levels of emissions, we have a slight delayed warming, first cooling and then delayed warming. But in the higher emissions levels, we have cooling, substantial cooling. And that is, of course, reflected in the ZEC, which we get in about 0.6 degrees of cooling, including internal variability. Now, looking at the special patterns of this ZEC 100 years after the emissions, the temperature response in the different scenarios shows some warming patterns over the North Atlantic in the lower emission scenarios, and some extensive cooling patterns in the same region for the higher emission scenarios. So we have a warming hole in the higher scenarios, expanding warming hole, and warming in the southern hemisphere. But in the lower scenarios, we have the building, the representation of a warming dome. I don't know if that is a term that's been used before, or if there is another term for this phenomenon, but the truth is that where the models showed a warming hole while the AMOC is declining, in the simulations, the stabilization simulations, we see a warming dome. The models warm up faster. And we look at the AMOC control in these high emission scenarios, and we see that while the AMOC doesn't seem to correlate with the global mean zero emissions temperature at any time. In the higher scenarios, we have a much stronger correlation. In the scenarios, the 1700 and the 2000 scenarios, we have a very strong correlation. So the AMOC does control ZEC, at least at the high emission scenarios simulations. Now, turning into the flattened experiments, I'm not going to go into the description of these experiments because actually it's been done by the previous speakers. But I'm going to say that we are particularly interested in how the ocean plays a role in the reversibility. And when we say reversibility, we are talking about temperature, surface area temperature reversibility, which is shown here. This is a figure from the Sanderson et al. Paper, which was recently it came out. And we see that all the models more or less show a degree of reversibility, which is of the order of 0.2 plus or minus degrees Celsius. And some models have a bigger hysteresis loop, and some models have much smaller hysteresis loop. So we want to see what the ocean's role is in this set of experiments, the flat 10 and the flat 10 CDR. The surface temperature change from the pre-industrial in year 100 of the flat 10, when we have reached the 1,000 petagrams carbon cumulative emissions, shows a warming hole in almost all the models, maybe except one. The strongest warming hole is in model CSM and GIS, but the other models do show consistent behaviors, even though more muted. In the Southern Ocean, we do see some models taking up carbon, some models, warming, and in some models actually slightly cooling. At the end of the flat 10 CDR, 200 years after we have started imposing the negative emissions, what we see is that most of the models show cooling in the entire globe, but we are seeing again the emergence of this warming dome at high latitude North Atlantic, especially in the models as the CSM and the GIS models, which had the strongest warming hole before in the ramp-up experiments. So this is a consistent behavior also across the models, but the magnitude of that varies. So what is this heat and carbon storage anomaly from the PI? How much heat and carbon is being stored after we have completed this hysteresis loop? Actually, we find that even though the temperature at the surface we showed that has a very small remaining temperature difference from the pre-industrial, the ocean stores a lot of the heat and the carbon that was released. 65% of the heat released during the experiments flat 10 and flat 10 CDR remains in the deep ocean below 1,000 meters, and about 25% of carbon is stored in the deep ocean, which represents a very long-term commitment of the ocean into global warming. Where does the heat and carbon enter the oceans in these experiments? And I will point you to the most important features. For the heat, the main sink for heat is in the North Atlantic. The Southern Ocean has a minor sink, and the models, some of the models disagree. This North Atlantic sink remains potent during the ZEC experiments, the stabilization experiments, but is muted and in fact reverses sign, meaning that the North Atlantic emits heat to the atmosphere in the CDR, at the end of the CDR. Again, the Southern Ocean sink remains somewhat the same, but there is a lot of disagreement between the models. In contrast, the carbon uptake occurs in both the North Atlantic and in the Southern Ocean. And in fact, at the end of the flattened simulation, the models show a more stronger uptake in the Southern Ocean. Both the North Atlantic and the Southern Ocean sink are being reduced in the ZEC experiments, and reverse sign emit CO2 to the atmosphere, as you've heard earlier before, almost symmetrically as in the end of the flatten experiments. The ocean emits carbon. The surface ocean above, obviously, the 200 meters. Looking at the relationship with the AMOC heat flux anomaly, both at the during the flatten experiments and the reversal, we have they are strongly correlated with AMOC. But for carbon flux is not correlated during the flat 10 experiments, and it's correlated strongly during the positive emissions of the CDR simulation. So that is represented in this flux, but in this plot, but it quickly saturates after the AMOC has completely recovered. By the way, the AMOC representation in the models is shown here. Flat 10, the first 100 years, the AMOC declines in all the simulations, and strongest in the GIS and the CSM model, and then recovers with a lot of variability, structural uncertainty, as we would call it, within the models. And in the flat 10 and CDR, the recovery is also very strong, and in fact, we end up with AMOC, which is stronger than the pre-industrial. Now, if we want to address the question, what is the relative role of heat and carbon uptake, we will use the linearized energy balance model as was obtained by McDougall et al. In 2020, and we include here a term for the emissions, the changing emissions. The heat uptake contribution, the cooling to the system, because we have the ocean takes up heat, the cooling due to or warming due to the land sink, and the cooling or warming due to the ocean sink of carbon. And lambda is the feedback parameter. What we are seeing is that, and we are not looking at which term is driving the delta T surf, the change in temperature after a complete round of flat 10 and CDR. We are only looking at the relative role of heat and carbon uptake and focused in two models, the GFDL ESM and the GIS model. And we see that during the ramp-up experiments, when we ramp up emissions to 1,000 petagram carbon, and for the first 50 years, the land and the ocean heat uptake and the carbon uptake actually act equally to cool the planet. But then in stabilization, the ocean continues to take up carbon, meaning cool the planet, but the net heat uptake in the ocean slows down, and that leads to a positive contribution to warming in the atmosphere. And this behavior is consistent between the two models. In the flat 10 and the flat 10 CDR, we see that similar behavior, obviously, for the flat 10 part of the simulation, and for the CDR, we see that the carbon flux, actually, the carbon uptake has a peak of cooling contribution to the global mean surface temperature, and after that point, it also slows down and reaches zero, consistent with the fact that we have emissions. And this, again, is similar behavior in both the simulations. One thing that I want to point out is that the role of epsilon in the relationship that we had before, which is the efficacy of the ocean heat uptake, this coefficient is usually computed based on 1% scenario, and it is considered to be a constant number. However, we are finding that it varies not only across models, but also across scenarios, and that should be taken into account. And I will leave you with a summary slide, and I can take your questions. Thank you.
I have a question. You just that last point that you mentioned, that the heat uptake efficiency is changing over time. Sort of how much is it changing, and do you think that that's related also to changes in carbon uptake, or are they separately controlled processes? Like, is it something associated with circulation or something else?
Yes, so definitely it is the change in the ocean heat uptake is related to the AMOC, because the main region, as I showed before, of heat uptake is the North Atlantic, and therefore it is affected by any changes in the magnitude of the AMOC. And as the AMOC becomes stronger and warms this part of the ocean, it will change the heat uptake. Now, in the McDougall formulation of the linearized model, energy balance model, these two terms, the heat uptake and the carbon uptake, they are separate. And so, yes, both of them are affected by the circulation, but not affect each other, or at least directly.
Next up, we have Jim Randerson.
Thank you.
Oh, perfect. Oh, is there a way to go backward? Yeah, got it. Okay. 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 Sorry about that. Okay. I can start here. This isn't the first slide, but it's okay. Great. So I'm going to talk about the chemical imprint of deforestation today and its work with Li Zhu at UC Irvine, and I'm really excited to try to collaborate here with the CESM group to try to understand better the fire contribution in the deforestation process. So the kind of the paradigm from both the synthesis by pan and also the global carbon project is that there's about 2 petagrams of carbon coming out from deforestation, and that's been pretty constant over the last 3 decades. And so there's deforestation going out, there's a carbon going into other forests from CO2 fertilization and other processes, and so the net's about 1.6 from this study. This is really similar to the Global Carbon Project 2023 and 2024, where gross deforestation flux is about 2/3 coming from permanent deforestation, which is pushing it into like large agriculture, large-scale commercial agriculture, and then they're shifting cultivations. Another third adds up to about 2 petagrams. Generally, in many parts of the tropics, fire is a primary tool to remove debris as you're pushing it into commercial agriculture. In the upper left, like you see all those little dots, those are fires around kind of when you see a square block in the satellite remote sensing imagery. Often the fires are ignited all at the same time, and it's a really different pattern than when you have a forest fire, which is shown in the right kind of blue bullseye, where like it'll start at a point and then the fire will grow outwards kind of every day, and it will create kind of like a tree ring, like a bathtub effect, where some of the trees will be killed during the day and then they won't be killed as much at night. And so fire is a key process. Same thing for peat in equatorial Asia, lots of draining and burning to improve the soils and the aeration for acacia and oil palm. And so this is more of a quantitative description of this, where you have, you know, up to like 10 or 15 years before a transition that you see. This is from a map of Biomas land cover time series. You see fires increasing, active fires measured by MODIS in the upper left panel, and then after the transition from forest to pasture, you see the fires decline. So say, well, what's the harvest piece of the deforestation flux? The pan paper has it being at about 0.09 or 0.1 petagrams of carbon. That's shown in the, there we go, here. Across the different decades, not really very little in regrowing forests, but intact forests. So this is about like maybe 5% of the total gross deforestation in the tropics. This is another synthesis from work from Yinan Baran, published in Science recently, and this is the total carbon flow into cities globally, and it's about 0.2 petagrams of carbon, 0.25. And some of that's coming from like paper and mid-latitude forests, so they're actually pretty consistent in terms of that flow. And so I've been working over the last 2 years to try to come up with a improved long-term time series of global fire emissions. Burned area is a lot higher than some earlier estimates. It's about 750 or 60 million hectares per year. Carbon is generally declining because we have more cows in the world. Like cows and fires are kind of interchangeable to a first approximation. So the more cows you have, like the fewer fires you have, because they both consume grass. So that's what's driving the decline in burned area. But the last 2 years, we've had enormous fires in both Brazil and Bolivia in 2024, and then Canada in 2023 and 2024. So in this inventory that we're putting together, if you look at the part of the emissions from fires, and we're trying to constrain this inventory using satellite data from MODIS of burned area, active fire observations from different sources, from MODIS, from VIIRS, and also using higher resolution imagery, we're getting only about 420 teragrams of carbon coming out from the sum of deforestation, tropical forest degradation fires and peat. So it's about, it's on the order of about 20% or so of the gross flux that's being projected in the carbon assessments. And you could say, well, there are a lot of assumptions in trying to come up with fuel loads and combustion completeness factors. Another approach that like Christine Wiedemeyer has really developed nicely is like using fire radiated power in active fires. You can say, well, what's the fraction of total fire radiated power that's coming out from these tropical areas? And it's also about, it depends on you if you correct for clouds, but it's about like 14 to 17%. So of the total emissions that are going in the system, it's really hard to change this ratio and have an imprint in carbon monoxide globally. You'd have to have a really a big imprint in the extratropics if you were going to substantially modify the tropical flux. Okay, so the science question is really what's going on here is if most of the permanent shifting cultivation are combusted, what's the imprint in terms of carbon monoxide and aerosol in the atmosphere? And so this was work done with E3SM. We did some experiments, and I'd love to work more with CESM to explore this and in the process of writing this up. So I want to work with people on it. Okay, so this is now in E3SM version 3 with the chemistry developed by Chitang. There's this is like the total fire emissions on the upper left, and then this component that's coming from tropical forest fires, deforestation, and peatlands is in the lower left. So it's mostly across the tropics. It's 420 teragrams a year. So here are the experiments. The main ones, GFED5 with GFED5 emissions, but all other sources from biogenic, also from fossil and other sources, methane oxidation. Then there's a no fire run. There's one where we just isolated we had all the other sources of imprint on atmospheric chemistry, but just the tropical forest fires. And then finally this final one is to try to like amplify the emissions from the inventory to bring it into agreement with with the global carbon assessments. So this is just to show that column mixing ratio, it agrees favorably. We're a little bit high at high latitudes compared to MOPID observations. Fire imprint is about like something on the order of 20%, and the tropical imprint is small globally, but it's important over the tropical forest areas. And I want to draw your attention to these areas of rapid land use change. I'm going to show you data from MOPID and from aerosol optical depth measurements from the Amazon, Congo, and Southeast Asia. So the baseline simulation with the inventory coupled to E3SM, you basically somewhat reasonably explain the seasonality and interannual variability of the carbon monoxide MOPID column over the Amazon. Central Africa, we're a little bit high, possibly from savannas. In tropical Asia, you see those big spikes from the El Nino draining and burning. And then if you look at the simulation where the emissions are tripled to bring it into agreement with the carbon budget assessments, you get the carbon monoxide column is much higher. It's not in agreement with the observations by about a factor of 2 or 3. Same thing happens for aerosol optical depth, where on the left-hand side, we have like the baseline scenario with about 400 teragrams of emissions going out. The right-hand one is where you get it up to about 1.6 teragrams with the purple line. And I'm not showing Africa here because the dust flux in this version of the model is being tuned. It was challenging you have to have your dust well represented to do aerosol optical depth in much of the Atlantic and across Africa. So the conclusions and future directions are that a successful deforestation and land use solution, it needs to match the tropical carbon monoxide, NOx and ozone and aerosol imprint. It could be that the global carbon project assessments of emissions are too high. It could be that GFED emissions are too low. The answer is probably in the middle. I don't think that wood product pools can be a big part of this difference. And so important future directions, I'd love to work and repeat some of this with CESM version 3. Want to try to look and revise some of the land use change product pool flows in the models. Look at it from Tropomi and really carefully assess some of the emission factor uncertainties that would be really important in kind of translating between carbon emissions and CO and aerosols. And there are dozens of studies that have tried to measure the chemical imprint of this, so there's uncertainty, but I don't think it's a driving factor that can explain a factor of 3 or 4 between the two approaches. So thank you.
I have a question. I'm curious about other aspects of atmospheric chemistry, like are there differences potentially in OH that would change the carbon monoxide response to the specified fire emissions?
I think the fires, like it would be a perturbation to the OH, but I don't think it would be enough. Like when you're over a source region, the carbon monoxide is very sensitive to the emissions. As you move into the global background atmosphere, then the hydroxyl radical response becomes more important. And so given that the lifetime's maybe like a month for CO, so you can get a little bit of destruction or if you have a different OH in the background, but it's not going to really affect things too tremendously in those regions. But it's a good question. Like the fires overall actually reduce the hydroxyl. They increase hydroxyl radical because these savanna fires emit a lot of NOx. But in the remote atmosphere, they consume hydroxyl radical because there's more of a CO imprint. Thanks.
Catherine Roki? Yes.
Hi, I'm Katie Grassi. I'm a postdoc at University of Colorado and University of Michigan. I'm a long-term visitor at NCAR, working with Will Weeder and Peter Reich, and we're going to talk about soil biogeochemistry. Okay, so since not everybody here probably thinks below ground all the time, I just want to talk about why do we care about soil biogeochemistry, and why is it worth representing in Earth system models. So first, soils are a quantitatively important part of the global carbon cycle. There's more carbon stored in soils than in plants in the atmosphere combined. And so changes in this pool can have implications for carbon climate feedbacks. Additionally, representing soil biogeochemical mechanisms can change answers in response to global change. So just as an example here, this is work from Terra et al. And looking at the effect of elevated CO2 in experiments and observational experiments on plant and soil carbon pools. The x-axis here is different mycorrhizal syndromes, which I think of as kind of a plant soil mechanism. And what you can see is that whether you have arbustular ectomycorrhizal fungi used to have different responses to the plant and soil carbon pools, right, to elevated CO2, suggesting that these kind of mechanisms can change answers. And importantly, for this mechanism, as an example, this mechanism is not super well represented in our models. And so I don't know if you'd like read this graph super clearly, but just note that the red modeled work versus the blue observed work is quite different, right? And so we're not representing that particular mechanism that well in our models. But fortunately, for CLM5, for the community land model version 5, we have the ability to assess soil biogeochemistry. So the default CLM5 model uses a century-like soil model, and I'll explain more about that in a little bit. Whereas we can also use CLM5 with this mimics model, this model that Will Weeder and others developed, that has some different kind of soil biogeochemical mechanisms represented. And so to look at these different soil biogeochemical mechanisms, we're going to do this within a single site experiment called Terracon, and this is a global change experiment in a tallgrass prairie up in Minnesota that's been going on since 2012. And in this experiment, they impose 4 different global changes. So they do a warming experiment by heating up the ground surface with these lamps and also the soil with heating cables. They do rainfall reduction with these like tent-like structures you're seeing in the background of this photo. They elevate CO2 just by piping in additional CO2 with these PVC pipes. And then finally, they add nitrogen just by fertilizing every year. And for this work, I'm going to focus on temperature and elevated CO2, and that's for a couple reasons. One, like these are probably our most certain responses to climate change, right? We're elevating CO2, and that's causing warming, and so they're interesting to study. And also their interactions might be particularly interesting to study because they might have kind of different effects on nitrogen cycling in particular, and so we're interested in that. And why I'm looking at this experiment in terms of soil biogeochemistry, if we look at observed results, we see that after 10 years, we see some carbon cycle responses that might be indicative of some soil biogeochemical mechanisms. So I'm going to show you a bunch of observational data looking like this. So it's going to be the carbon pool under elevated CO2 on the y-axis, ambient versus elevated temperature on the x-axis, and then nitrogen treatment in the colors here. And so what you'll notice in this kind of boxed area is that leaf carbon increases under elevated CO2, regardless of temperature, or sorry, under elevated temperature as well, but regardless of nitrogen treatment. But if we look at soil carbon under elevated CO2, we see that its response depends on the amount of nitrogen. And to me, this kind of could indicate a soil biogeochemical mechanism at play here. So when we're in a nitrogen limited situation, so this pink bar here, elevated CO2 causes a greater nitrogen need in the plants, right? And so you might break down soil organic matter to get that extra nitrogen, and that might reduce soil carbon. Whereas when nitrogen is readily available, that might not happen. And that's a mechanism known as like priming or nitrogen mining in the soil world. And then you see a similar response for root carbon, maybe indicating changes in root allocation, maybe allowing for that kind of microbial breakdown of soil organic matter. And so basically all I want you to get from these kind of plots is that like there's probably some soil biogeochemical mechanisms at play here, which makes it interesting to look at whether different soil biogeochemical models lead to different global change responses. Okay, so to that end, the question here is, does soil biogeochemistry alter global change responses? So as I mentioned, we'll be looking at the warming and elevated CO2 experiments, and then a control with no global change, as well as the interaction between warming and elevated CO2. And again, that interaction is really interesting to me because of maybe these nitrogen effects, but also because these models are rarely confronted with interactive global change effects, and so that's also interesting to look at. And as I mentioned, we'll be using CLM, what I'm calling CLM Century, with a century-ish soil model, and then looking at CLM mimics. And I'm just showing you the soil submodels here, and you can see they look different. So Century is kind of more of this decomposition cascade, whereas mimics has these explicit representations of microbial pools. Let's see. You can, yeah, these microbial pools here. And that can allow just for some different plant soil feedbacks. And so because of that, we kind of expect different global change responses for these different models. Okay, So first we calibrated CLM Century. So here's out of the box parameters at the single point site we're looking at here. And you can see that we're underestimating root carbon, overestimating soil carbon. But thanks to the PPE tools and the PPE team, it was very easy to calibrate CLM Century. So we just alter the decomposition rate, photosynthetic dependence on nitrogen, and then the root to shoot ratio to get a model that looks a lot better to start with. For calibrating CLM mimics, we also start with lower shoot and root carbon and higher soil carbon than we want. And what we did is first use the same plant parameters as we did for CLM Century, so we were just looking at soil biogeochemical mechanisms. Then we also altered mimics parameters, but unfortunately we don't really have a quite calibrated model yet. We changed decomposition also for mimics. We changed absorption, which is just like, it can affect how long it takes for soil carbon to turn over. And then we also changed microbial turnover. And we see that soil carbon is pretty good, but we're still not growing our plants very well. So this is something I need to work on. And so just take the mimics results with a big grain of salt because it's not quite calibrated yet. But I still want to look at global change effects, so we'll look at that. So I'm going to show you several plots like this, looking at different carbon pools, and then looking at the observations, and then with Century, and then with mimics. So the control will always be in blue here, and the goal is to kind of compare these global change effects to the control, which is why there's that blue line there. And then the warming's in yellow, elevated CO2's in green, and then the interaction is in red. And so you'll see for shoot carbon that warming and elevated CO2 both increase shoot carbon by about the same amount, but the interaction also increases it just slightly more. And with these interactions, I'm particularly interested in whether they are additive or synergistic. And so if you had an additive interaction, you'd expect that the warming and elevated CO2 effects would just add together to get the interaction effect. But here you're seeing that the interaction is not as strong as it would be if it was an additive effect, so that's a synergistic effect. Okay, so looking at the model results. For the Century version of the model, we see that the elevated CO2 effect looks pretty good, as does the interaction, but the warming effect is actually negative in the Century model, or with the Century model. And interestingly here, the interaction is quite additive, right? So if you were to add the warming and elevated CO2 effects, you kind of get the interactive effect. For mimics, we actually see something pretty similar. So for mimics, we see decrease under warming and then increase under elevated CO2 in the interaction. And again, this is relatively additive as well. Okay, so for root carbon, we see a similar kind of response in the observations where warming and elevated CO2 both increase root carbon, but the interaction effect again is not quite additive here, but also positive. For Century, we see a very similar response as the above ground carbon, with that decrease under warming, increase under elevated CO2 in the additive interaction. But for mimics, we see relatively similar, but this time we see like basically no effect of warming on root carbon in mimics, so a little bit closer to observations, but again, pretty similar. And a slightly synergistic effect if you squint a little bit, but really a pretty comparable. Okay, and then finally for soil carbon, this is where we see again this increase in warming and elevated CO2, but maybe your most synergistic effect you're seeing yet under the interaction, where the interaction is actually having a lesser effect than warming or elevated CO2 alone. CLM Century again looks very similar to the above ground and below ground plant carbon pools, where you see a decrease under warming, increase under elevated CO2 in the additive interaction. But with the mimics model, we see something very similar to the root carbon pool, where warming doesn't really respond, elevated CO2 increases, and then you see, again, this very slightly synergistic effect with mimics. So overall, I would say you have pretty similar responses from mimics and from Century. And again, remember that mimics is not quite calibrated yet, so take that with a grain of salt. Okay, so looking forward, I want to know if these results persist with a better calibration of mimics. That's a big question. And then secondly, if they do, can we get our models to produce these global change responses, particularly that interactive response that's synergistic and not additive? And can we do that through parameter or structural changes? And there might be some hope for parameter changes having this effect. So here you're seeing an old version of my mimics plot that has different parameters. Again, this is a not very well calibrated model, take that with a grain of salt. But just interestingly enough, like there is this really big interaction effect that you could not predict from the warming and elevated CO2 effects. And so that to me suggests that maybe by changing parameters, we could get something that looks more like the observations one, but maybe more interestingly, it might tell us about like what soil biogeochemical mechanisms are important based on what parameters we need to change. So takeaways, currently the soil biogeochemical models provide pretty similar answers. They're not really providing very different answers under global change, but again, not quite calibrated yet. But maybe with different parameterizations, we can get some variation and some potential synergistic interactive effects. That's all I have. Thanks.
I think the mimics deltas looked much smaller than, you didn't focus on this, but besides the soil. So if you go back not to a non-soil, yeah, the mimic's response looks much smaller than the century response and much smaller than the root. Do you read anything into that?
Yeah, I guess just a reminder that the mimics results are not very well calibrated, so that's one issue. But yeah, potentially there's some feedbacks going on, and that kind of points to that soil biogeochemical mechanism, right? Like if we have this priming effect, maybe some of that carbon that would be used for growth is actually being used to recruit microbes to get nitrogen, right? And so maybe that you'd expect less of a response in mimics given that its potential to maybe better represent these priming effects. Maybe.
It seems like a couple of the pools really respond to warming, but the models show a kind of a muted or a very small response or a negative response. And I was curious, are these like C4 or C3 grasses, and is it a rest? What do you think is going on that the models are having a hard time with the warming response?
Yeah, so they are C4 grasses. I will say that we use a C3 grass in the models because of some easier parameterization. But I guess what I think is going on, and this is maybe my nitrogen bias, is that I think warming has been shown to pretty consistently increase nitrogen mineralization, and so I think that's allowing for that to happen in our root carbon and our plant carbon in the observations, but maybe that's not super well represented in our models. That's my guess. Yeah.
I mean, I guess since so much of what you're looking at is like the plant responses, I just wonder if you do you think is this enough to just look at the century versus mimics, or do you need to sort of blow up the whole thing, look at because a lot of this is about allocation, right? And so that's going to be the common between both of these models, right? So
Yeah, no, that's a fair question, and with that calibration, we were trying to keep the plant parameters the same to try to just look at soil biogeochemistry, but you're right that we might not be able to get there with just soil biogeochemistry, particularly if it is particularly a root allocation kind of situation. So yeah, that's a good point. Yeah.
And so for the warming signal, which doesn't look right really across anything, is it plants that are really showing that? Is it coming from the plant response to warming, or is it coming from the soil BGC response to warming not being right?
In the observations, or
well, no, all of them are showing either a decrease
or no
relative warming or
response.
not much of a change, and the observations are showing quite a strong change.
Yeah.
So yeah, have you looked at where the source of that problem is?
Yeah, not so much yet. Definitely something worth looking into, and yeah, my guess is nitrogen, but I don't have evidence for that yet. Yeah.
Okay, so we have time for discussion now. We could talk about the talks, additional questions for our speakers. I was hoping we could pull up our remote speaker on the screen if possible, if she's still there. Natasha's still there. And also just comments or ideas that people have for ways that the BGC working group can coordinate these activities. I think we've seen, global scale emissions-driven types of simulations. We saw from Jim thinking about interactions with atmospheric chemistry, and we saw thinking about BGC in the context of where is carbon going on land. And then our second half of the session will be more ocean and polar. But I was wondering if folks wanted to have any comments they wanted to pose to the group or questions they wanted to pose to the group on any of these topics or to our speakers. Okay. It's like deciding if I should wait you all out or start a question.
Yeah, well, I like thinking of Anastasia's talk. It's really interesting, like if the thermal haline, like in some of these models, is really close to shutting on or off. It feels like if we go into that place where we start stabilizing emissions or they start coming down, that we might be in a time when there's really a lot more like climate variability maybe than we've had in the past, where it was interesting to me to see how the ZEC response seemed like it was really tied to the strength of the shutdown of the AMOC. And so I guess my question is more just like, what are the implications for interannual variability and that like the broader system of the AMOC shutting down like that?
Yeah, I don't know if Natasha is still there, if she wants to offer an answer. I was also struck by the ocean circulation aspects having this big imprint, and I'm not following that literature carefully, but I know there's a recent paper that just came out showing that the amount that a model responds in its AMOC is very related to the initial depth of the mixed layer in the North Atlantic to begin with. And so, are there just different states that these models are starting in that is then controlling this larger system response, which will imprint onto ZEC? So again, I have lots of questions about how much is being driven, how much of this response is going to come from aspects of the physical climate versus aspects of carbon cycle. I feel like we have a lot of work to do to figure that out. Is Natasha there? Does she want to comment? Okay. Yeah.
I have a question for James about the fire and its imprint of the atmospheric chemistry. So you show a map of the contribution of the fires to the tropospheric CO column, and I see a lot of reds in the north hemisphere, which indicates like it can contribute by up to 30%. I guess that's for all the fire types, but I wonder if you only look at like the fires as a tropical region, will there have the equal contribution to the CO for both hemisphere, or there's also some hemispheric asymmetry?
A lot of emissions from like agriculture and boreal fires that I think are pushing it up, and then also the tropical fires I think change the hydroxyl radical in the north by emitting that CO that's getting out to the northern hemisphere, so it's lengthening the carbon monoxide lifetime. In the tropics, I didn't have a time to go through it very carefully, but we did this one run where it was just the tropical deforestation and peat, and then also degradation fire, flux, and that one, in the areas that I was looking at in those boxes for Moppet, that was most of the imprint. So there's like savanna fires and things, but it really was the tropical forest fires that are generating most of the interannual variability and seasonal variability over the main land use regions. But I think globally, that imprint is mostly savanna, and then in the north added with some temperate and some boreal, I would say. So it's good.
One thing I was just thinking about, seeing your talk, Jim, and then I know there was a talk in the other session on chemistry about interactive fires, and maybe we should think about next year about having a little bit of a joint session between BGC and chemistry, because I think there's quite a few intersection points that we're not having those conversations. When would it be nice to try to do that? I was sort of thinking about in Abby's talk. I was trying to understand. You were showing the flat 10 land carbon uptake over the growing period is, I think the range was about 200 petagrams, but then the CMIP, it's like 1,000 petagrams difference across the land models, right? In terms of their cumulative carbon. And I can't remember the time scales. That might be all the way at the end of like 2100. Anyway, so is that, flat 10 map doesn't have any of the land use. So is this, can you go all the way and say that like land use is like generating a majority of the uncertainty in the land carbon sink trajectory, or is that going too far?
That's a good question. I feel like Jim has thought about a lot about this too, and maybe Charlie. I certainly think that land use is a big component of it. I don't have a number for it, if either of you do. Yeah. Yeah, it's an open question, it's my take on it.
Yeah, in some ways, like that tropical deforestation flux has been like it's like the residual term, like that there's like the people are measuring these sinks across the northern forests, and then you have to close the budget, and so you come up with this flux, and that shifting cultivation piece is really uncertain. And so I would say, I don't know, Charlie or other folks, like a factor of 2 on the size of the flux, something like that. And I think we're poised to make a lot of progress at that, on that in the next 5 years. Like there's amazing now, like land cover products that are coming out, not only the really nice one from Hansen and the University of Maryland group, but there's another like tropical moist forest Landsat time series of land cover that I think is really powerful. So yeah, hopefully we'll make some progress on that. But
I guess I'd say one thing I'm excited about in that space is FATES being able to do land use, because you'll get a different distribution of where the carbon is in the beginning that will then inform, as you go through land use change, how much carbon is coming out. So I just feel like, we have sort of modeled estimates of what the contribution of land use has been, but those might change.
Yeah, but fundamentally, if the input forcing data set for land use is wrong, which Jim is suggesting it might be, then it doesn't matter what FATES is doing more accurately. So yeah, I think we need to explore that. One thing as a point of reference for everybody is that, it looks like what's going to happen for CMIP7 is, the issue with the fire emissions, that they went from like relatively smooth to like wildly varying to back to relatively smooth during the satellite record. If you actually look at the land use time series record in the same way, it has a lot of that same character to it. And there's some really wild swings in the LUH2 data set, especially coming from the tropics. And I think what we're kind of leaning towards is having essentially a smooth version of the land use change as well, deforestation, especially in the tropics, as being the forcing. So we kind of get rid of those wild, which are maybe just satellite measurement error or something like that. So, but the mean will still be the same, but it'll be smooth this time. So.
Has there been an argument that affects the? I think I've seen Jerry and John talk a little bit about this, but why does the variability? I understand the variability is. It's like kind of like volcanoes, right? Like we put in the volcanoes in the historical record, but we never put volcanoes in the future. But we should, because we know that there's going to be a volcano in the future. We know that actually the distribution of sizes, right? But there's an argument out there, maybe someone can explain it. How does the variability affect the mean state? I don't totally understand that well, or is it more about just explaining the trend over the satellite record? But I've heard that, Dave, right, that there's somehow it's really important to not put in the variability, but we are putting in the variability for volcanoes. So why are fires different, back to you, than volcanoes? If we put in the volcano forcing with variability and we don't smooth them out, why do we need to smooth out the other ones? Does that make sense?
Yeah, and I'll interject and say there is a talk about fire aerosols at the end of the next BGC session, and how do we make assumptions about future fire aerosols, because apparently the assumptions are that they're flat going into the future, which probably isn't right.
Well, to partly answer your question, I think at least in the historical period, all the volcanoes are in there, so it does have the proper, in quotes, interannual variability coming from volcanoes. Whereas with the fire, it goes from smoothly varying, just estimates from whatever offline models into this really wildly varying. And so fire is more variable on a year-to-year basis, I guess, than volcanoes. Maybe, I don't know. And then in the future, though, you're right. It's a problem with volcanoes in the future. And I know people have talked about, putting in like random volcanoes but I don't think that's happening in CMIP7, but it's, that's come up before. So yeah, it's just, this is an issue that, and it seems to not filter down. I mean, that the first attempt at the CMIP7 fire emissions was the same variability again, even though we had shown it had a huge imprint on the simulations. And so I think now it's been that they're giving the smooth version, but and then I was actually in another conversation with some other atmospheric emission, and they had the same thing. That had, maybe not having the same total big imprint. And I said, it needs to be consistent, but even CMIP trying to be all coordinated, they can't quite get communication across all the different teams that are building these data sets. So yeah, it's an issue. But
Yeah, I guess what I'm hearing is the question of, you can't have it go from smooth to really highly variable. That messes things up a lot. Why do we not make it highly variable in the past based on some distribution? Yeah, Jim's questioning why it's a big problem that it goes from smooth to variable.
Look at the papers. I've heard the argument. I've forgotten that the actual, but it shows up really clear when you do the analysis. You can really see like a really distinct change. John has a paper on it. Yeah, pretty sure it's John's paper. I can't remember who the lead author is.
He's here.
He's here. Yeah, he's here. He could explain it.
Not in this room, but
I was like, I bet that it will be in this talk at the end of the session as well. Yeah, I think it's because partly just because the variability is so gigantic relative to the smooth version. But there's also these questions about what to do in the future. Like, is there going to be no change in fire emissions in the future, or should we be representing something like that? Anyway, this is sort of specific to fires.
It's interesting for international variability, right? Because you don't have, it can't hear you on the internet.
Yeah, and I'm having trouble running back. I'm just going to.
It's interesting for climate extremes and for interannual variability in the future that if both fires are smoother than they should be and there's no volcanoes, then like it makes you wonder, like with respect to like these climate whiplashes and things that people are starting to talk about, where you go from a drought to a flood. Maybe we're not even capturing the full magnitude of that if we're not putting in these kind of variable forcing pieces. I don't know. Okay, sorry.
Yeah, and so the obvious response is that's why we'd like to include the interactive fire aerosol emissions, which we have the capability of doing, and Peter Lawrence's simulations with CSM2 are doing that, and we have the talk that was going on in parallel was trying to analyze the impact of that. So, it'd be nice to do, everything is happening too fast and also too slow to see if we'll be able to do that, but we definitely have the capability of assessing it. We have these set of simulations now to assess, what is the difference in variability that we're getting from having interactive fire aerosol emissions. The volcanoes is another story. I can't answer that one, but with the fire, we can do it, except for the fact that I would guess that our interannual variability in fire is probably too low, because we don't really seem like the giant fires. We wouldn't be able to capture like the Australian fire thing or the big Canadian fire. Is that what you're just going to say? Yeah.
Well, I was going to ask.
I don't know if we've done a proper detailed assessment, but my just guess would be it would be too low, the interannual variability.
No, like if it's a Peter,
I was just going to say that the talk that's in the chemistry session right now is showing that there is actually a negative feedback from fires, because when it gets hot and dry, you have fires that give cooling. So it actually suppresses some of the interannual variability in temperature. But yeah, it's also one of those things that if you have it modeled, you then have continuous your interannual variability is continuous from the historical period, current period, and then into the future projections. Because the fire model is then driving your aerosols, which is kind of like one of the, I guess, benefits of going down that pathway. And yeah, and the reason why the interannual variability is so important is there's a nonlinearity between the aerosol emissions and their interactions with clouds. So you could have like a background state where, so like the mean is very different from like going from high to low. When you have a very clear period, you have a very strong warming response. Whereas you saturate when you go to a high period, so like you don't get the I guess the same cooling as you do the warming from the difference. That's really it.
Thanks for the good discussion. I liked Dave's idea of having a joint session with more chemistry and aerosols, and it feels like it's time to sort of I know there's many things to understand within BGC, but where it's clear that these factors are interacting across other parts of the system as well, beyond just thinking about, say, carbon and nitrogen species. So that's a great idea for going forward. Thanks everyone for a great discussion, and we'll be back after the break for a joint BGC polar group, which again includes at least one talk about fire as well as things about the ocean. So see you in a bit.
discussions, and I had thought that 2 months ago.
Is it working? Okay. So yes, welcome back. So this second half of this morning session is going to be polar BGC topics, quite a variety and fun talks. And we'll start that off with Kara Nissen, who is presenting remotely. And okay, take it away, Kara.
Thanks, Kristen. So I'm assuming you can see my slides well. If not, protest now.
It looks good.
Perfect, thank you. So yeah, hi everyone. I cannot see anybody of you. I hope you see me well. First of all, thanks to the session organizers for giving me the opportunity to present my work remotely to you today. I'm very sad that I cannot be with you in the room today. So yeah, my name's Kara Nissen, and I've recently joined the faculty at the University of Amsterdam. However, the project that I'm going to talk about today is the result of my previous position at CU Boulder. And I would first like to acknowledge all my co-authors listed at the bottom here, some of whom I believe are in the room with you today. So this project focused on the impact of storms on Southern Ocean biogeochemical properties. And I am assuming many of you know, but some in the room might wonder, why would you look at storms in the Southern Ocean? And I think the title slide already gave an illustration of that. I just pulled the wind speeds of a day a couple weeks ago in May. And you can see like two nice storm systems here in the Atlantic sector and the Indian sector of the Southern Ocean with pretty high wind speeds. And overall, the Southern Ocean is considered a very, very windy place where storms are, what I would argue, omnipresent. So the map that I'm showing here is an analysis I've done based on JRA reanalysis data. So I took sea level pressure data and tracked storms in those. And what is shown here is the median number of days for any given location in between any two storm passings. And this is expressed, in days. I've did this over a 20 plus year period. And what you can see here is that we have really vast areas of the Southern Ocean where storms pass at least once a week, if not more. So it's really an area where storms kind of pass all the time. Which makes you wonder how ocean properties, in particular, in my case, ocean biogeochemical properties, are impacted by the passing of these storm systems. So this study is about the impact on phytoplankton dynamics in particular, and storms can really impact phytoplankton dynamics through a variety of processes that I'm trying to illustrate here. Of course, we all know storms change winds, change the cloudiness, and so from an ocean's perspective, storms really induce mixing and also change light availability. Or the light that is available to these photosynthesizing phytoplankton. I recognize that, of course, storms also induce precipitation, but this is not the focus of my talk. So in the context of phytoplankton, when we look at upper ocean phytoplankton, I mean, storms can really have a variety of impacts on phytoplankton, and then I've illustrated here. On the one hand, the mixing can cause a downward mixing of plankton, phyto and zooplankton, from the surface to the deep ocean, but can also induce an upward mixing of plankton to the surface from lower levels. While this mixing is occurring, of course, the distribution of important biogeochemical properties, such as nutrients, changes. So ultimately, it's really competing effects of changes in light availability and nutrient availability in concert with the changes in the vertical distribution that causes any change in phytoplankton that we see when a storm is passing. So the synthesize is really changes in phytoplankton growth that can be directly induced by the passing of storms. It can be a vertical redistribution of existing plankton biomass, and it can also be a change in the predator-prey interactions when phytoplankton and zooplankton are brought into contact more or less when a storm is passing. So in this study, we look a bit at the drivers, but ultimately we want to also quantify how storms contribute to subseasonal variability in chlorophyll and total biological carbon cycling. To do this, we use CESM2 in this case. In particular, we used an ocean sea ice biogeochemical setup, so an ocean-only or ocean sea ice-only simulation that is forced with the Japanese reanalysis product JRA. And I want to just point out here that I'll be mostly talking about what I call the low-res simulation, which is the standard resolution of CSM2. In the corresponding paper that's currently in review and Global Biogeochemical Cycles, we also looked at Kristen's high-res resolution, so the 10th of a degree. I will not present it in this talk in the interest of time, but just want to point out that the results are qualitatively similar in both resolutions. The special piece about the analysis that we've done here is that the version of CSM2 that we used for this study also includes the satellite emulator that was developed by Jenna Clow, who's a PhD student at CU Boulder in the group of Nikki Lewandowski. And so what she has done is really to implement a satellite into CSM that samples CSM's chlorophyll fields in the same way or in a very similar way to the way real-world satellites sample the real-world ocean. So the output of CSM that we get when having this emulator activated is really the standard chlorophyll output, so the normal full field output that we're very used to analyzing and seeing. But then we get a second set of fields of chlorophyll, and I've just stolen one figure from one of Jenna's paper here, which just illustrates what the output of the synthetic chlorophyll observations look like. And these resemble really the fields of satellite chlorophyll that you would look at if you look at real-world satellite observations. So this way, we really have a way of kind of analyzing the model truth, so the full field CSM outputs, and compare them to what the satellite would see in the real world. And here we account for kind of missing data when clouds are present and when the solar angle is too low for the satellite to see anything, which is of course relevant in the context of polar waters. With the setup, the first step in quantifying the oceanic signature of storms is to track storms and kind of identify when they occur. And for that, I used an existing software package called Tempest Extremes, which is has been developed and is maintained by a group at UC Davis, Ulrich et al. And this really looks at the sea level pressure fields in the JRA and then gives you positions and times of all the storms in your data. Once I have those tracks, the goal is really to isolate the variability on synoptic timescales in the storm impacted area. And what I mean by that in this context is the radius, the 1,000 kilometer radius around each storm center that I have identified. To get at the synoptic timescales here is actually, I think, not as straightforward as one might think. And in the community, there's a lot of slightly different ways of doing it. But what we've done here is a kind of a three-step process. In the first step, we subtract daily climatology from our daily averaged CSM output fields, which really leaves us with the non-seasonal chlorophyll variability. In the second step, we then take these anomalies that result from step one and kind of average these for the 5 days preceding any passage of a storm. And we call this the pre-storm conditions. And the choice for 5 days is really motivated by the plot that I've shown you earlier, really that it seems to be a good measure to kind of at least minimize the probability that two storm systems impact on the signal that I'm seeing. I then subtract the two fields that I get from step 1 and 2, and I'm left with the variability on what I call here synoptic timescales. We do this for a period from 1997 to 2018 for all storms that pass through the area south of 40 South. Important to note, we only include ice-free waters here, so any point that has sea ice cover, we mask for this analysis. We just want the open ocean signal here. And this ultimately leaves us with approximately 10,000 storms to analyze for this time period. So let's jump into some results. Here I'm showing the average storm-induced surface chlorophyll anomaly over all the storms. So all seasons, all locations, all of them, for the standard CSM chlorophyll output. So this is the standard chlorophyll field that you get with any CSM simulation. And if you compare kind of the numbers that are printed along these contours, which denote the absolute chlorophyll concentrations in these storm-impacted areas, to the color bar, the range of the color bar below, you quickly realize that, well, averaged over all storms, the imprint on surface phytoplankton appears to be very small. The signal is kind of interesting with a negative anomaly in the northern part and the positive in the southern part, but just comparing the magnitude, you would argue that, well, do storms really matter? And I'll get back to that in a second. First, let's just compare to what the synthetic satellite observations tell us. And of course, this is now my subjective perspective, but looking at this broadly speaking, at a first order, I would argue that the synthetic observations can broadly capture the sign and the pattern with the negative anomaly in the north and the positive in the southern parts. But there is a lot of patchiness, of course, that needs to be acknowledged. But overall, the synthetic observations are able to get the average signal quite okay. If I then look at the distribution across all storms, so not averaging just all storms into one, but kind of now calculating averages over the whole storm impacted area and doing this for every single storm. So getting the average surface chlorophyll anomaly for each storm and plotting those in a histogram, this is what I'm getting. So while in the top right, what I've shown you earlier, the magnitude of the color was very low compared to the absolute isolines, here we see that the distribution has actually kind of quite long tails towards quite significant surface chlorophyll anomalies. And I think that's easily understood. Like here, I mean, in the top right, and also here, we include storms in all seasons, but we know that phytoplankton dynamics are highly seasonal. And a storm passing in winter is very unlikely to cause a very large chlorophyll anomaly in the absence of light, or at least in situations where light is very limiting. To get at one of the questions I posed in the beginning, we can compare kind of the storm-induced anomalies to the result of what I called step 1 in our analysis. So we can compare the storm-induced anomalies to the total non-seasonal variability in chlorophyll to really get at a sense for how important storms are in contributing to this local and temporal variability. This is shown in this histogram here. And if you just expressed in percent, and you can do the math and can show that it's more than 1/3 of the storms that explain most of the non-seasonal chlorophyll variability. So again, while the average chlorophyll anomaly appears small, there is a significant number of storms at the tails of the distribution that are significant at a local scale and contributing to non-seasonal chlorophyll variability. And therefore, I'm now going to just jump into a subset of the storms, which I call the high impact storms. And here I'm just showing you the 10% storms that the storms that cause the 10% largest negative chlorophyll anomalies. And again, I'm first showing you the model truth here. And I would like to first point you again to the isolines here, which again show the absolute levels of chlorophyll and the scale of the color bar. And now we immediately see that this is at least on the same order of magnitude. So I would call this a significant impact in terms of just comparing chlorophyll to the storm-induced anomaly. We can then look at different fields to get a bit of a better understanding of what drives these here negative anomalies. And what I plot you here is the anomalies in wind speed and mixed layer depth, calculated in the exact same way. Unsurprising, I mean, the winds, especially in the northern part, causes very strong, excuse me, positive wind speed anomalies of up to like 4 or 5 meters per second, on top of the overall already kind of quite high wind speeds of about 12, 13 meters per second, which induce like a deepening of a mixed layer of up to 15 to 20 meters. And I'm not going into the details here in the interest of time, but we can compare these anomalies that we get for phytoplankton growth rates. And we can see that actually it's the wind speed induced mixing that causes these chlorophyll anomalies. In this case, it's really a downward mixing of surface chlorophyll rather than a local reduction in phytoplankton growth. We can again compare this to the synthetic satellite observations, and here I would argue, I mean, yes, I mean, we see a lot of blue on the right side of things, but I would argue here that the agreement is worse than we had in the average picture. And we conclude from this that our ability to quantify how much high impact storms contribute to local chlorophyll variability is limited with satellite data. So the smaller the subset of storms is that we're interested in, the more likely it is that satellite observations will be skewed one way or another. We then also wanted to look beyond just surface chlorophyll because ultimately we're interested in how phytoplankton contribute to the global carbon cycle, the Southern Ocean carbon cycle. And so as a metric for biological carbon cycling, we looked at net primary production. and just asked the question of whether we can infer anything from the surface chlorophyll analysis for integrated biological carbon cycling, or integrated MPP in this case. And what I'm showing you here is two storm-induced anomalies, the left one or the middle one here for surface NPP, and then the right one for total vertically integrated MPP. And for the surface NPP pattern, I would argue that there is some similarities here between the chlorophyll signal and the surface NPP. So there is an indication that the surface NPP signal is actually also dominated by the downward mixing of carbon in this case, as opposed to the growth factor that goes into the calculation of NPP. But if we look at the vertically integrated MPP signal, the maximum or the minimum chlorophyll anomaly here, the most negative anomaly, is actually not in the same location as for surface MPP and chlorophyll. And if we compare this to the anomaly in incoming PAR, so the change in light availability as induced by these storms, there's really some nice agreement in the location of where the most negative anomalies are. So here we show that for vertically integrated NPP, it's really the change in light availability that dominates the response, and that it is difficult to derive storm imprints on total biological carbon cycling based on satellite-derived surface chlorophyll data alone. So that already brings me to my summary. I'm just going to leave these four takeaway messages up here, and just want to point out that we have an ongoing project which is led by Katie Christensen, who's a postdoc at CU Boulder, who's then looking at using floats to detect storm imprints in the Southern Ocean, as floats, of course, have the advantage over satellites that they really give us an idea of what happens at the subsurface and not only at the surface. And with that, I thank you for your attention, and I'll take any questions.
All right. I have the microphone for questions. Do we have a question or two for Kara? All right, it doesn't look like there's any in the room. Thank you so much, Kara. Oh, look, you can see me now, maybe.
I can see you.
Thank you so much. We're going to move on to the next speaker. So that's Shan Lin. She's going to come up here. And for everyone's reference, I will run the microphone around for questions after this, too.
Okay, so... Okay. Hi, good morning, everyone. I'm Shani Wang from Xiamen University. Today I'm presenting the work from my students, Shiyao Zheng. She simulated marine nitrous oxide and also trying to estimate its offsetting effects during iron fertilization experiments. Not this one? Okay, so my talk will cover these parts. First, I will briefly talk about the background. So we all know the ocean plays an important role in absorbing anthropogenic carbon dioxide, but meanwhile, it also releases about 20% of nitrous oxide into the atmosphere. And nitrous oxide, of course, is the third most important contributor to the radiative forcing of long-lived greenhouse gases, and also it has significant potential in stratosphere ozone depletion. In the ocean, nitrous oxide production is mainly linked to nitrification and denitrification as a byproduct of nitrification, as well as intermediate product of denitrification. But still, the processes are very complex, and still it's very difficult. At least right now, we still have a lot of uncertainties in terms of the detailed contribution of nitrification and denitrification to the N2O production in the ocean. There have been quite a few field campaigns trying to measure the distribution of N2O in global ocean, and they identified hotspots in the global ocean. As you can see, there are like high values from the low oxygen water, such as Arabian Sea and Eastern Tropical Pacific, as well as some well oxygenated waters. And they identified factors affecting the N2O distribution in the ocean, for example, the oxygen concentration, temperature, wind speed, and etc. And there have been some previous modeling efforts trying to incorporate INTOL in Earth system models. I'm just showing you some examples here. And most of those modeling work try to parameterize INTOL production based on temperature and oxygen concentration or consumption rate. There are a few modeling efforts trying to tie the INTOL production directly to nitrification and denitrification processes. But in this study, we decided to start from the simple parameterization method. Here, what we tried two parameterization methods. The first one is based on the empirical relationship built by Butler et al. In 1989, which basically assumed the production of INTOL is largely related to the nitrification processes and also with some influence of temperature on the renormalization rate. And here's the equation, and we also try to parameterize the parameter value here. And the second method is based on the oxygen consumption, which consider the production. Well, the equation includes two parts. The first part is with a constant background yield for INTOL production that is largely linked to nitrification process, and the second part has oxygen-dependent yield, which has shape like this. Means we will have enhanced INTOL production at low oxygen concentration, which includes some impacts of denitrification. And here is the values of parameters we use in the second parameterization method, in which fall in the range of previous modeling work. And here I'm showing you the simulated RC pressure difference of INTOL. And as you can see, we also have got those hotspots at, like, say, Arabian Sea and East Tropical Pacific, and which is similar to the observed distribution pattern, and yet we also get a little bit negative that piece INTOL at really high latitude, but we don't really have observational data to constrain those values yet. And we calculate some standard deviation, correlation, and for those two parameter methods, the values are very similar, but in terms of the detailed INTOL production, there are differences in low oxygen condition water, as you may expect. And here is the simulated INTOL fluxes at surface, and from those two parameter methods, and also in comparison with previous modeling work, and the pattern in general looks similar. And our distribution pattern, the INTOL flux pattern, is also very consistent with the pattern of POC flux in marble. With that, we decided to use it to identify the offsetting effects in iron fertilization, because iron fertilization has been proposed as an efficient strategy to promote biological carbon pump and reduce atmospheric carbon dioxide concentration, but it was also suggested that INTOL production during iron fertilization process may increase, because no matter is as a byproduct of nitrification or the intermediate product of denitrification, both has a strong control by the supply of organic matter and also the renormalization processes. So we define our study area in the Southern Ocean, because the Southern Ocean is the largest Asian LC region, and also we have several strengths in the Southern Ocean and divide Southern Ocean into distinct zones which can have significant different response to the iron fertilization experiments. We expect they may also have different, the INTOL offsetting effects may also be different in those different zones. So here is our experiments. Well, we use the CSM 2.1.3 version of the code, and then we use the GRA, run 4 cycles as spin up, and in the fifth cycle, we introduced the parameterization for N12 production and emission. And in year 281, we started the iron fertilization experiments to really separate the impacts of N2O in different zones. We divide the Southern Ocean into 3 zones based on the location of France, and calculated using the sea surface height. And then the 3 zones are sub-Antarctic zone and the polar frontal zone and Antarctica southern zone. And we have several sets of experiments. In the first set of experiments, we have continuous iron fertilization over 25 years. And the amount of iron fertilization is based on some previous iron fertilization, in situ iron fertilization level. And also in the second set of simulations, we try to fertilize the ocean for 1 month and 1 year only. And then in the third set of experiments, we define some 5 by 5 degree patches and want to see whether the size of the patches of iron fertilization can have different impacts. Okay, so in this talk, I'm mainly showing you the results from the first set of tests. And here on the left upper panel, I'm showing you the differences, the time series of differences in dirt PCO2, DPN2O, and POC fluxes, as well as the N2O offset effects. And the upper row is from the SAZ and PFC as well as the AIC. And the lower figure shows you the changes compared to the control run in small phytoplankton, in diatom in the middle, and as well as the total net primary production. So as you can see, also summarized in the figure, that when we fertilize the ocean, we have an increased iron supply, which promote the net primary production and decrease the surface PCO2 in the ocean, and also enhance the POC flux, which lead to increase the production of N2O, and of course increase the N2O emission in the Southern Ocean as well. And also, even though we only fertilize in the distinct zones, the impacts in biological production spread over, extend over the distinct zones where we have iron fertilized. And also, initially, the pattern for a significant drawdown in surface PCO2, like we see a big change in dirt PCO2, and then later it gets back a little bit, which agree with previous studies as well. So, yeah, and that's why we also see a significant increase in terms of the N2O offset effects. Okay, and then we calculate the offset effects in terms of radiation benefits from those three sets of simulations. In the number range from 5% to 25%, also a large range, depending on the fertilization location and the length period of the fertilization, as well as the spatial extent. And the figure on the left, even though it's a tiny table, it has a lot of information. Okay, so the first column here shows you the averaged offset effects of N2O over 25 years, okay, and in different zones. In the second column, the upper number shows you the offset effects within the first month if we only fertilize for 1 month. And the second number, the lower number, shows you the offset effects for a year. And then in the third column, that the upper number shows you the offset effects in a year, and then the lower number shows you the offset effects over 25 years. And if we compare the lower number in the third column with the number in the first column, that you can see the impacts of size or the patch sizes of fertilization. So it seems even within the same zone, if we fertilize over the entire zone, then the offset effect gets larger. Okay, and also for PFC and AIC, we have the offset effects larger over time. So initially, we have significant drawdown in carbon dioxide, but later the drawdown gets smaller, but POC flux is still high, which promote a high production of N2O, which lead to overall larger offset effects if we fertilize the location for a longer period of time. And so now I'm just going to briefly conclude the estimate here. First of all, we think the offset effects of nitrous oxides should be considered if we decide to use biological carbon pump as our method to do the MCDR. Okay, so because both processes, both trace gases are linked to the supply of organic matter in the carbon, the biological processes. And also in our experiments, we consider the polar frontal zone may be a better place to do iron fertilization in the Southern Ocean, considering both the efficiency of carbon removal and also the amount of offsetting effects of N2O. And also we think relatively medium-sized iron fertilization patches may be more efficient than the overall large scale strategy. And so that's it. Thank you. And questions?
Thank you. Thank you so much, Shanlin. I don't know if this microphone's working. Are there any questions in the room?
Hi, Shanlin. I might have missed this, but you were showing a larger effect in, I think it was the SAZ versus the PFC, and those differences between the zones and your nitrous oxide offset, are those because those different regions of the Southern Ocean have a larger areal extent, or are those areal normalized such that you're getting more of an offset per square area in one zone versus the other?
So when we calculate we didn't normalize based on the overall area, but we calculate the overall carbon removal effects and also the N2O emission effects. So that's consider sum over the entire zone. And in terms, let's see. You see the way how we calculate the offset effects based on the potential in radiated forcing. And so I would say the number is irrelevant to the areas.
Okay, thank you.
All right, is there another quick question in the room? All right, if not, thank you, Shanlin. Our next speaker is Laura Landrum, and she's gonna talk to us about Antarctic icescapes and ecosystems.
Okay, I should stand by the microphone. Before I get started, I really want to do a shout out and a thank you for combining the Polar and BGC work groups into a session. We have done quite a few projects that overlap in terms of resources and people and ideas. And this session, it's great. Thanks for doing this. This work is collaborative and represents work by myself as well as Alice DeVivier, Kristen Krumhart, Marika Holland, and Zephyr Sylvester. And first off, Just really quickly, I'm going to step you through some main features of Antarctic sea ice, and then talk about what I mean by sea icescape in the marine ecosystem, and then look at how the CESM2 is performing. And we have, in general, found that the CESM2 is a very useful tool for a lot of different biologically related studies in the Antarctic ecosystems. And we'll wrap up. Joey, how do I play this? Do you want to play that? Can you play that for me? Uh-oh. Uh-oh. While he works on that, I'm just going to talk a little bit. There we go. This is a video of Antarctic sea ice. Just want you to sit back and look at it for a bit. This is from satellite images, and that sea ice expands and contracts. This is from 1979 to 2023. It expands and contracts a great deal, and it's often called the heartbeat of the world. One time a year, goes out to its max, back to its minimum. At a maximum, it's about 18 million square kilometers, minimum about 3 million square kilometers. Sea ice in Antarctic is primarily seasonal. It's built and melts in one season. Some exceptions are like the Weddell Sea that has some perennial sea ice. And then notice that it's not just ice extent or area. There's lots of complications in that sea ice. You notice around the coast, you see some dark areas. Those are polynyas, areas where the water tends to be open and surrounded by ice and land. Those are hotspots in the biological ecosystem. For comparison, that's 15 million square kilometers of sea ice that is built and melt every year. The United States as a whole, land area included Alaska, is 9.1 million square kilometers. Canada, 9.9. So about 1.5 times the surface area of the United States or Canada that is built and contracts every year. Ecosystems are dependent on it. They've evolved to be ice dependent. And okay, now we can go ahead. Can we go ahead? There we go. There's that seasonal sea ice extent on the left-hand side. That's from the observations. The blue line at the bottom is where we are now. I want to remind you a couple things of the importance in the global system. When we talk about doing societally relevant work with our climate models, sometimes we don't talk about Antarctica because it's not owned by any one country. It doesn't have a city, it doesn't have high populations. On the other hand, that region of the globe is very important for climate regulation in many ways. 30% of the CO2 that's emitted by the burning of fossil fuels is absorbed by the ocean, 30%. Of that 30%, 43% is absorbed in the Southern Ocean. It's a huge source of taking up this CO2, much of which is sequestered in deeper waters that form around the Antarctic continent, go to the bottom of the ocean, and can be sequestered for time frames up to 1,000 years or longer. Furthermore, about 83% of the increase in the atmospheric heat due to anthropogenic release of fossil fuels is taken up by 83% of the heat that's taken up by the oceans. The oceans work as air conditioners to a large degree. 83% of that heat is taken up in the Southern Ocean. It's very important. Likewise, the land ice around Antarctica is extensive and thick and has the potential to impact sea levels. And there's been a lot of research in the last decade that indicates that many of these glaciers in Antarctica, they are held in place by buttresses of floating ice shelves and or sea ice that help prevent interaction of relatively warmer, deeper water coming in to interact with that and melt that ice. And ice can melt much more rapidly with warm water than it can with air. So there are questions about what happens. Is it possible for these ice buttresses to collapse catastrophically or rapidly? And sea level rise, we're used to thinking of happening on centuries or longer timescales. Some recent studies have suggested maybe we should reconsider that from the perspective of the Antarctic. And Antarctic sea ice has undergone huge, unprecedented changes in the last 5 years. Changes in variability, changes in persistence, and we think it might be a regime change which has the potential to impact this as well. And then finally, Antarctic ecosystems are unique, they're endemic, they're extremely productive, and they are highly sea ice dependent. So these are some of the many reasons that we use the CESM to look at the climate in Antarctica and how things are affected. This picture up here on the left is showing a bloom of phytoplankton in a polynya around the Amazon Sea area. I'm looking, and when I talk about polynyas, I'm just going to talk about coastal ones. Coastal polynyas form in the winter, and fall when these very strong winds, katabatic winds, come off the continent, and they blow sea ice away faster than it's made. And so you end up with open water, extremely cold temperatures, and sea ice is readily made again. Some of these polynyas are called sea ice factories. So part of that 15 million square kilometers of increase and decrease over the year is happening in these polynya areas. Did I go back? Yeah, there we go. They also are very productive. They're biological hotspots. That picture, Tish Yeager, who took that picture, is a biological oceanographer. And I remember her describing her first research cruise to the Amundsen Sea, where she ended up in a polynya at the time of a bloom, and she said nothing in her work ever prepared her for what she saw. It was so murky and so green, and she was just astounded. She's been going down there ever since. Sea ice is also important. It serves as a substrate. Predators can hunt from it or hide from, prey can hide from predators. It serves as areas of mating, molting, chick rearing for penguins. It's critically important for krill, both in maintaining water temperatures and as a substrate over the winter. And if you want more details on that, I've now extended my biological understanding of krill. I'll send you to Kristen. This is another picture of a polynya in the Ross Sea, and that's a satellite image showing the phytoplankton bloom in the Ross Sea. So does the CESM2 have polynyas in it? Does it have polynya-like features? This figure is actually a satellite image of sea ice concentration, and we've developed an algorithm that can identify polynyas in gridded data products. And you'll see the outlines here in orange are outlined coastal polynyas, areas of low sea ice, open water or sea ice, at least 10% or more of the time. And this figure shows the same thing. The orange lines are areas of polynyas in the observations. The dark brown lines are areas of polynyas identified in the hindcast, the forest ocean sea ice hindcast of CESM2 over the same period. And CESM2 does indeed identify polynya-like areas, features in this. And are they productive? Yes, indeed. They are areas of high productivity. This figure is showing the annual net productivity in Antarctica. The darker green areas are higher productivity areas. And you'll note that those line up often with polynya areas. Another way of looking at this is looking at both the total and the area average net primary productivity. The total, southern hemisphere primary productivity in the top, area average in the bottom. In the sea ice zone, which we define as 85% or higher sea ice concentrations in the winter, is in the light blue, and productivity in the polynyas is in the orange and the green. And just the take-home picture from this is that productivity within coastal polynyas in the CESM2 is about twice as high as it is in the sea ice zone. And because it's twice as high, even though polynyas only occupy about 10% of the sea ice zone in area, they contribute to about 18% of the productivity. And when we look at how this is changing in a changing climate, apologies for too many figures on one, but here we go. Upper left is that same thing. This is from the CESM2 large ensemble with the beginning of the 21st century on the left, the end on the right, productivity when the sea ice zone is the blue and the polynyas, the orange and the green. And note that by the end of the century in a changing climate, we have significantly reduced sea ice. Productivity in polynyas is still quite high. It's about the same magnitude as at the beginning. It's not really changing. But the contribution of marine productivity from polynyas to the total productivity is decreasing. It's primarily due to the fact that productivity in the sea ice zone is increasing. More sea ice is melting, you're getting more light, less light limitation, and a higher productivity. And in fact, that bloom in the sea ice zone, not polynyas, sea ice zone, is also moving in time. So it's no longer occurring a peak in January, but a peak in December by the end of the 21st century. The time series below shows the polynya areas. They are in time from 1850 to 2100 from the CESM large ensemble. Those are two different metrics for identifying polynyas. I'm not going to go into that because I'd put you all to sleep and you'd be here forever. But in general, that area is decreasing a little bit. And this, before I get into that, a lot of that work has been used by Alice de Vivier and her team in developing a tool to help give scientific advice for policy planners who are looking at regions around Antarctica for establishing marine protected areas. And I also want to give a shout out to everybody who worked on developing MARBLE and making it so that we could add different phytoplankton and zooplankton class sizes, which has been critical and necessary so that we then have model output, we can run offline fish models. So Kristen did a poster yesterday, and if it's online and you haven't looked at it, I would recommend you do that. Looks at emerging climate signals from plankton through fish through penguins based on the CESM and offline fish models and work with penguins and Yep, just about out of time. And then with another thing that we've looked at is relationships between sea ice concentration and productivity. These are correlations between the spring, so October, November, December, sea ice concentration from the CESM2, large ensemble, and the spring productivity, so October, November, December NPP in the top two, and the summer bloom in the bottom two. And then on the left, it's from the beginning of the it's from 1950, sorry. And on the right is from 2100. And note that these relationships are pretty constant in time. So higher sea ice concentrations in the spring are associated with lower spring blooms, and higher sea ice concentrations in the spring are associated with higher summer blooms in general. The contour lines on this are showing this marginal sea ice on that outer line is contouring the 15% ice concentration. The inner one, closer to the continent, is the ice pack, 85% and higher. There is a region in the Weddell Sea where you have a negative relationship between spring sea ice concentrations and summer bloom. That's because the sea ice concentrations there are still so high that it's not reduced enough to give more light. However, in this region, I'll skip that one because I'm running out of time, sea ice is thinning. So these are figures of light limitation term. The light limitation term is a term that goes from 0 to 1, 0 being completely light limited, not enough light for any productivity, 1 being complete, total available light. Light is not at all limiting, and I colored it so that the purple to green goes at about half. That contour on there, the beginning of the 20th century on the left and on the right, is the ensemble mean contour for the 50 centimeter thick sea ice. And you'll note that a lot of those changes in light limitation are determined by sea ice thickness rather than concentration. So in summary, the CESM2, well, yeah, actually, yes, there we go. If you have any questions, I'm be happy to take them. Thank you.
Do we have one quick question for Laura? All right. Thank you, Laura. You can find her around at lunch and other times too. So we're now transitioning to Courtney. We've mostly talked about the Antarctic, but Courtney is going to talk to us about both the Arctic and the Antarctic.
Hi, thanks so much. Yeah, and thank you to all my collaborators on this project. So in polar ecosystems, the environment's very light limited, as Laura nicely demonstrated a moment ago. In winter months, depending on latitude, there's no availability at all of light, and even when the light returns in the spring and summer, sea ice and snow can block it from reaching the surface of the ocean. So when we classically think about phytoplankton blooms in the Arctic, I, at least, have this kind of mental image, that only around the time of sea ice breakup and retreat do you get a big phytoplankton bloom that's drawing down nutrients and fixing carbon. In the 2010s, there was a research cruise in the Arctic that attempted to look at these pre-bloom conditions, and they anticipated seeing something like this image. Under ice, you can see a small amount of light kind of penetrating into the surface of the ocean, but the water is blue, which means that there's very little primary production happening. And what they instead observed was images more like this, where you have this murky pea soup green water that's under a full meter of fully consolidated ice. This bloom has ended up being one of the largest blooms ever observed anywhere in the world's oceans. And yeah, it was in this very improbable environment that we kind of anticipated didn't produce big blooms. And since this first observation of a massive under ice phytoplankton bloom, blooms like this have been observed pretty ubiquitously through the Arctic. In some places, they account for more than 50% of annual primary production as well. So this is the Arctic. What about the Antarctic? Might be a logical next question. Well, there have been essentially no in-person observations of blooms like these in the Antarctic. But a recent kind of set of observations using BGC Argo floats indicate that while sea ice concentrations are still relatively high, phytoplankton biomass increases pretty substantially and approaches kind of bloom-like levels. So there's increasingly evidence that the Southern Ocean might support these big under-ice phytoplankton blooms as well. And that's particularly true in the Ross Sea region, kind of at the bottom of this diagram. So I was really curious to understand, these blooms I think have really reshaped what our kind of understanding is of when phytoplankton are growing in these polar regions. Perhaps thinner sea ice, different ice conditions allow these blooms to happen largely in this part of the year that we can't well observe with satellites, and we don't have a lot of boats going to explore these places. So I was really I still not get to my questions, my goodness. A consequence of this kind of misunderstanding that we have of these marine ecosystems is that when we typically think about a bloom, we think about it happening in pretty warm waters, where a burst of production can fuel zooplankton grazing. In the Arctic, it's largely copepods at the top, and in the Southern Ocean, it's largely these krill. And that leads to a lot of food available to upper trophic level organisms. But if we're kind of shifting how much productivity is happening in this under ice period, that means that it's happening at really low temperatures, minus 1.8 degrees. And that will prevent a lot of zooplankton grazing. They can't grow to consume as much biomass as being generated, which could have very sad consequences on upper trophic level organisms. And that kind of maybe fundamentally alters our understanding of the carbon balance of these ecosystems, because that means that more of this fixed carbon that phytoplankton are generating could be, in the Southern Ocean especially, sequestered, or especially in the Arctic and coastal regions of the Southern Ocean, could fuel a lot of benthic productivity. So provide food for clams and amphipods, and in the Arctic, animals like this walrus. And this, of course, could also lead to changes in nitrogen loss from the sediments, like Shanlin so eloquently explained earlier. So I finally was very curious to understand more about these blooms and their impacts on annual net primary production. I was specifically curious how much phytoplankton NPP is generated under sea ice in the Arctic and Southern Oceans, how that might be changing over time. There are kind of indications that these blooms are not something that happened historically, and that they've only started to occur as sea ice has thinned. And so I was curious to investigate that, as well as how they might change by the end of the century. And then under what kind of environmental conditions under ice blooms are forming in these two different regions was also a curiosity of mine. So in order to answer these questions, I relied on a very special run of CESM. It was a version 2 less melt parameterized run, so it has more accurate representation of Arctic sea ice, and has 4 phytoplankton and 2 zooplankton functional types. It's very special because it has daily output of light at the ocean surface, and also the fractional coverage by each sea ice thickness category. And that allowed me to go and back calculate light limitation terms under different sea ice thicknesses, and also in open water. And then I was able to use that to partition daily NPP into kind of the NPP generated under sea ice and in the open water within each grid cell. Okay, so using this method, how much NPP did I find was generated in the Arctic and Southern Oceans? I'll show you first a figure from 2025 of the proportion of total NPP generated under sea ice. So yellow indicates that almost all NPP happening at that location was generated under ice. And as you can see in the Arctic, there's a region off the coast of Greenland and in the Canadian archipelago that really lights up bright yellow. This has very thick multi-year ice, and it is very persistent. So it's perhaps not surprising that this is a place where there's a ton of under ice production. But even further out in the Arctic, it accounts for a pretty large proportion of total under ice NPP. It's about 23% of annual production that's generated under the sea ice. In the Southern Ocean, nothing pops out quite the way that the waters north of Greenland do, but there's a fair amount of productivity off the West Antarctic Peninsula as well as in the Ross Sea. Overall, this region has about 19% of total annual NPP generated under ice. And what's perhaps surprising looking at this image is that the two hemispheres have about the same contributions to total net primary production generated under sea ice. So about 130 teragrams of carbon per year in each region. Okay, I was also curious how under ice NPP is changing over time. So here I'll show you a plot of from 1916 to 2100 how NPP is changing. In the Arctic, we can see that it's pretty stagnant for maybe the first almost 150 years of this time series, and then it kind of rapidly declines between 2050 and 2100. So that kind of idea of these blooms not being observed in the past is not really borne out by this modeling study, or actually a bunch of other modeling studies as well. Everyone has found that the reason we didn't know about these happening is just because we didn't observe them, not because they weren't happening. In the Southern Ocean, the net primary production doesn't undergo too many changes over the first part of the time series, and then it kind of drops off much later, maybe 2070 or 2080, there's a decline. So we can see that over time, in the future, net primary production during the under ice period will decline in both hemispheres, more so in the Arctic. So I was also curious about the environmental conditions that allow for these blooms in the two different regions. CESM uses 5 different sea ice categories, ranging from the thinnest ice, which is 0.6 meters thick or less, to the thickest ice, that's 3.6 meters thick, and I've got that in navy here. And when we look in the Arctic, we can see that about a third each of the annual net primary production is generated in the thinnest ice class, the second thinnest, and the third thinnest. So this shows us that actually these blooms can be generated under pretty thick ice, the same as we've observed them in the real world. In the Southern Ocean, however, only the thinnest ice is really kind of allowing these under ice blooms to form. So almost all of the production's happening in that thinnest sea ice category. I also looked at the concentrations of sea ice where this under ice productivity is generated. So I calculated how much, this is just for the ice-covered portion of each grid cell. But I split it off into grid cells that were either 85% or greater sea ice covered. So this is kind of the fully consolidated sea ice zone. And then in lighter gold, I have the 15 to 85% sea ice cover. So this is the marginal ice zone. This is where sea ice is rapidly retreating. And then finally, the open ocean with less than 15% sea ice cover. And in the Arctic, we can see that about half of total under ice NPP is generated in that fully consolidated zone, much like the observations have indicated in the field. In the Southern Ocean, however, the conditions that allow for under ice blooms are quite different. They're largely generated in this marginal ice zone environment. And that's also kind of borne out by these BGC Argo floats. They largely find these blooms in 40 to 60% sea ice coverage, so within that 15 to 85% window. Okay, so in summary, this work I think demonstrates to us a couple things. Firstly, that there's about 260 teragrams of carbon per year, perhaps, of net primary production generated under sea ice, and it's pretty split between the Arctic and Southern Oceans. And this is a major challenge for satellite observations in the regions because satellites can't see any of the productivity that's happening under the sea ice. So this could lead to huge misestimates in certain regions of productivity. This also shows us that NPP didn't really change much over the 1900s and early 2000s, but is likely to really decline over time in both hemispheres. And I think it also highlights some of the conditions that allow for under ice blooms and how they differ between the two hemispheres. So I found that under ice NPP in the Arctic is generated under this fully consolidated, relatively thick sea ice, but in the Antarctic, these blooms are largely generated in thin ice in the marginal ice zone. And I think this work overall has some pretty big implications for our understanding of the carbon export and trophic transfer in these ecosystems. Yeah, and so thank you so much for your time. I welcome any questions.
All right. Thank you, Courtney. Do we have any questions?
Hi, Courtney. Thanks. That was a very interesting talk. I'm largely curious whether, given that there's different proportions of net primary productivity under different concentrations or thickness categories between the two hemispheres, are we talking about like similar organisms that are responsible for the net primary production, or like is the basically identity of who's doing the producing important between the two hemispheres?
Yeah, that's such a great question. In the model space, we found that diatoms were largely responsible for both blooms in both hemispheres. They, I think, accounted for like 80 or 90% of under ice productivity. Observationally, in the Arctic, they've also been diatom dominated. In the Southern Ocean, the singular observation we have of an under ice bloom is it's like with nanoflagellates, and it's kind of under landfast ice. It's very weird, which I think highlight, and then the bioargo floats can't really as effectively give us species composition. So I think that to fully answer your question, we need a lot more observations in the Southern Ocean, but great question.
Hi, Courtney. Thanks for the presentation. It was great. The decline of under ice productivity, if you normalize that by the ice area, what is the trend then?
Yeah, I think it's increasing relative to the ice area, but I'd have to double check that. But it's in this environment where total productivity is also increasing, so it's becoming a lower and lower proportion of the relative, it becomes lower in terms of its contributions to total production by the end of the century as well.
All right, thank you. So next we're going to shift to Christina Black, and we're going to start to think a little bit more about things that happen on land as well as oceans.
Yeah, hi, I'm Christina. I'm a postdoc here at NCAR. And I study things that are a little different. I'm not an Earth system modeler, but I'm interested in applications of model outputs to try to understand how wildlife respond to their physical environment. So I work under this project called Rising Voices Changing Coasts, and the purpose of this project is to bridge Western scientists with indigenous communities. And within this project, I work with the Alaska Hub, and I put together a tribal advisory panel that works with me, and they come from indigenous communities from different regions around Alaska to try to help me identify research directions that are more regionally relevant for them, and also to help me contextualize my findings given their multi-generational knowledge of their areas. And so when trying to decide what to study that's relevant to them, the most obvious candidate is Chinook salmon, also known as king salmon. It's the big salmon that's historically had these massive runs that's been sustaining the indigenous communities that are pretty far off the road systems for thousands of years, but in recent years, those populations have been crashing. And there's a lot of debate over what's causing the crash. A lot of the scientific literature suggests that it's climate change. And so I was interested in starting a project looking at how Chinook salmon might be adapted to their environment. And so to study this, I start with looking at their genetic structure. And so for this, I have a sample set of about 27,000 salmon that were collected at around 180 spawning locations in the rivers around Alaska. And then their DNA was analyzed at 300 loci across the genome. And this genetic data was produced by the Alaska Department of Fish and Game since 1987 or so. And take these landscape patterns of genetic divergence and try to correlate it with some Earth system model output. So for the rivers or the spawning locations, I'm looking at various variables related to precipitation, river temperature and flow. And because you all might be aware that salmon are born in the rivers and they swim out and they spend about 5 years in the ocean and then they go back up the rivers to spawn, the ocean plays a big part in their life history as well. So I'm going to look at the ocean conditions as well. I haven't gotten to that, so this presentation is just about their river environments, the spawning habitats. And so I try to use the model outputs to predict the genetic structure to understand how they might be adapted to their local river conditions. And the method that I use this is essentially a version of random forest with multiple jackknifing replicates, but what this graph shows here is the important variables that can predict the genetic structure. And so on the x-axis here, this shows the importance of each of these variables to predicting the genetic patterns, and the most important variable that I have is the range of winter air temperature, which can predict around 20% of the genetic variation. And then the next most important is elevation, and then the range of summer air temperature. And then I can look at the gradients of these variables and try to figure out where are some ecological thresholds on the landscape where you can see the genetic turnover happening, where you can see populations diverging. And so if I look at the range of winter air temperature, which is the most important variable, and I plot that gradient, so here the cumulative R squared is like the same as the importance in the previous graph. But I can see that it really jumps up when the range of winter air temperature is around 15 to 20 degrees Celsius. So on the landscape where the range of winter air temperature starts to exceed that value, you would expect to find a different genetic population of salmon. And you can also see that for the second and third most important variables that the gradient is a little more gradual. It's not like a sharp environmental boundary. But I can use the combination of all of these important variables to try to infer where these environmental boundaries occur on the landscape and predict what the genetic populations look like in rivers where we didn't sample. So this is a PCA where every point is a river in Alaska, and they are colored by what I predict their genetic assignment to their genetic population is to be. So there's like a green population, a blue, pink, light blue population, and overlaying that, the arrows show the important variables in the previous slide and how they might be driving genetic differentiation of those rivers. So for example, the range of winter air temperature, which was the most important variable, might be, does this work? Cool. This might be driving divergence of the light blue and green populations, and elevation might be driving divergence of the dark blue and pink populations. And I can move these points onto the map to see where the boundaries exist. And so if you all are familiar with the geography of Alaska, this is like the Cook Inlet area. It seems to be a unique genetic population here that's divergent from this area, which is hard to tell in this color. This is gray. This is the Copper River drainage. And then across the Yukon, where elevation seems to be the best predictor that I have, you can see that there's a shift around here from the pink population to the light blue to the dark blue. And so we can predict based on the river conditions what we think the genetic makeup of these populations would look like. And then it's also interesting because for each of these variables, we also have the mid-21st century prediction of what those variables might look like and how the river conditions might shift into the future. This is what these maps show is essentially like the Euclidean distance between the map I showed previously, which is like the salmon responses to historical conditions, and then take the distance between that and what we predict the rivers to look like in the mid-21st century. So under a moderate warming scenario, we can see that the areas that are lit up like orangey yellow, that these are what we call high risk, meaning that this genetic population is expected to be mismatched to their future river conditions. And this area is Bristol Bay. And then under the high warming scenario, you can see that a lot more areas light up, but I think we don't talk about this scenario anymore. So for the moderate warming scenario, where Bristol Bay seems to be high risk, look deeper into that and try to predict what is going on in Bristol Bay using the same method. So this is another PCA where every point is now a river in Bristol Bay, and the way that you can read this is that the rivers that are closer together are more genetically similar, the ones that are further apart are more genetically different. And then I try to predict the multi-dimensional structure using the same environmental variables. And the important variables in Bristol Bay, or the most important variable in Bristol Bay is the change of winter stream temperature over time. And if I look at where the threshold is for this, you can see that it really jumps up whenever the slope is like slightly more than 0.01. So this is the best predictor I have for MDS1, which is the axis that explains the most amount of genetic variation. It explains 46% of the genetic variation. And then I can also look at this variable on the map and see where those vulnerable areas are that have a slope of winter stream temperature greater than 0.01. And one of the advisors on my panel is from an indigenous fishing community in Bristol Bay and is very well connected with the people there. And so part of what she helps on this project with is I can talk to her about trying to understand what they've been seeing in this area and trying to really narrow down the important variables that might be more explanatory. So the change in winter stream temperature over time, after talking to her, it does actually seem like it makes a lot of sense. But if it didn't, it could be correlated with something that's actually more important that I don't have captured here. So it is helpful to try to talk to people that like live here and experience this, and maybe she could say that like, well, actually the stream temperature isn't changing over time. It is. So that was actually really nice to hear. And the last thing I'm looking at also with the same data is if Bristol Bay is predicted to be mismatched to their future conditions, where else could they go? And so here I've highlighted in like yellow or light green where the mid-century best conditions are going to be for them. And so it kind of looks like the best area is like this Cook Inlet area, but they would have to get around the Big Alaska Peninsula. I don't know how likely that is. They could also potentially go up further inland if they could make it that far, and these areas look a little better. And there is some evidence that salmon aren't completely tied to their natal streams. They have sometimes just gone up different streams, so they are somewhat adaptable. They can choose to go someplace to spawn where they weren't born, so there's some potential there. And the last thing I want to talk about is that there are some caveats to my results. So everything that I've shown you so far are correlations between historical samples of salmon and the model outputs, but in order to actually be sure that like the range of winter air temperature actually matters to salmon, that would have to be experimentally validated. Also, I kind of touched on this, but some of the variables that I'm looking at, they might be correlated with what's actually important, but not the actual variable, but it is still helpful to try to figure out what the spatial patterns are. Also, I'm looking at 300 loci that are spread across all the chromosomes, so I'm assuming that these are linked to genes that are like useful. I'm not looking at any specific genes that we know respond to winter air temperature or something like that. So that's another assumption. And then lastly, the ocean obviously plays a huge role. They're living in the ocean for 5 to 7 years of their life. So I still need to look into that to understand more about what they might be adapting to. And I think I'm running low on time, so I'm gonna skip over these parts that I put in and quickly talk about my takeaway points. So firstly, genetic divergence in Chinook salmon is correlated with their local river conditions across Alaska, so they might be adapting to their local spawning habitats. And the statewide genetic patterns are most correlated with the range of winter air temperature at their spawning sites. And the findings that we have at regional scales are consistent with so far the conversations I've had about indigenous and local knowledge. Some populations are expected to be more poorly matched or maladapted to future environments than others, but there are places where they could potentially go if they chose to, if they were able to. So I would really like to thank everybody who's like helped me to figure out how to approach this project in the most ethical manner, and who's working on it with me. So I'll go back to this, and thank you.
All right. Thank you, Christina. Do we have any questions in the room?
Thanks so much, Christina. I'm really curious if there have been observed issues with Chinook salmon anywhere in Alaska thus far, and like does Bristol Bay have recruitment issues already, or are other places observing challenges already?
It does, yeah. Bristol Bay has had, it's one of the biggest areas of the population collapse. So they've been having fewer salmon return to the streams every year, fewer escapement in the spring. And part of the complications around there, which are the slides I skipped over, was that it's also a big commercial fishing area. So right off Bristol Bay, that's where like a bunch of big trawling fisheries are. They think that that might be contributing to it too. So that's pretty hard to disentangle, and that's something I can't account for. But yeah, Bristol Bay is having a big collapse.
All right, got another one?
I noticed there's a big sort of blank spot up on the North Slope. I mean, I guess there's been some stories of some salmon maybe reaching up to these communities on the North Slope. Is there any evidence of that, or?
Yeah, there's been some recent observations that Chinook salmon are suddenly showing up on the North Slope. Those, the river conditions there are outside of the parameter range of the samples that we had that were collected historically, so they didn't show up, or they didn't get included when I was trying to predict where they might go. But yeah, I guess it's interesting that, like I mentioned before, they can choose to move somewhere else, and if it's starting to become more favorable on the North Slope, they can figure it out, it seems.
All right. I think that we're going to go ahead and move on, but we can talk. All of a sudden, this is off. If you have any other questions for Christina with this work, please go ahead and find her. The last speaker in this session is Ed Blanchard-Wigglesworth, and he's going to be talking to us a bit more about Arctic fires and, fires and how they impact the Arctic.
Cool. Do I flip slides for this? Yes. Cool. Well, I'm Ed. I quickly want to acknowledge my co-authors, Patricia Durapentini and Dagen Friesen. And if you need to rush to lunch, then the one thing to remember is in the title. If we plot a time series of the biomass burning emissions, both in observations and in CMIP6, and we do that up to 2014, we get a time series like this. So CMIP6 models did not use active fire models, so they are where you need to prescribe them biomass burning emissions as kind of forcing or external files, and this is what looked for the historical period, and the 97 to 2014 time period, this is when we had GFED, like satellite observations, so that's why we have a bit more interannual variability, and you can see that the red and the blue time series overlap each other, which is what we expected. For the future scenarios, for the future runs in CMIP6, this is what the time series looks like. And by the way, I'm showing here black carbon as a proxy of all biomass burning emissions, but there's a lot of other species, but they're all fixed factors of each other. So if I plotted, for example, SO2 or organic carbon, the time series would basically look the same. So this is what we did for the 21st century in CMIP6. And so you can see it's almost a climatology flat trend, and value is kind of typical of the sort of early 21st century. If you add the recent observations, this is what it looks like. There's been a huge increase in observed boreal fires. If you take the average of the last 8 years since the 2015, the future runs, it's a 160% increase. This increase in boreal fires has been attributed to warmer summers, earlier spring snowmelt, less sea ice, all kinds of factors that we expect to keep contributing to more fires, or at least an enhanced boreal fire ecosystem. So there's been a very quick divergence here between the real world and how we put fires into CMIP6 21st century. We already see a sort of footprint in the aerosol optical depth from the fires. What I'm plotting here are the mean summer, so June, July, August, aerosol optical depth in the kind of in the early period on the top left, and then the last 5 years in panel B there in the middle top row, and the difference is in the top right panel, and you can see those kind of hotspots of increased aerosol optical depth over Siberia and Canada, or North America, but also extending from Siberia northward into the Arctic. If you plot a time series of both the boreal and the Arctic mean aerosol optical depth in that kind of lower middle panel on the right, you can see there's been a significant increase of the aerosol optical depth, both over the boreal region, but expanding into the Arctic, especially when we have years with big Siberian fires. And if you take the zonal mean of these changes globally, there's actually been a reduction in aerosol optical depth over China, I think due to legislation there. But you can see the increase around August, like late summer in northern latitudes, and that's coming from the fires. Okay, so what did we do? We have basically rerun new simulations with CSM2, where the only thing we change compared to the CSM2 large ensemble is the biomass burning emissions in the boreal latitudes, so from 56 north to 70 north, and we've created a new forcing kind of a new emission files based on the observed trends for each grid cell between 1997 and 2023, and we've extrapolated those into 2060. So we focus here on the next few decades, right? So we have new runs between 2015 and 2060. that, at least for the first few years, do follow the observed increase between 2015 and 2023, and then extrapolate linearly to 2060. And all species that are released by fires are included here. So not just in these simulations, I first show you here the mean summer, the column burden differences between our new runs. We have this 9-member ensemble and the CSM2 large ensemble. So you can see, we have this increase in these different aerosols, black carbon on the left, organic carbon middle, sulfates on the right, and you can see those two regions of enhanced fires, Siberia and Canada, but you can see that those aerosols, they don't just stay there. They are, they're advected, and you can see an increase more or less north of 40 degrees north, right in these aerosols. If you take the mean zonal difference in the aerosol optical depth in these runs from CSM2 lens on the bottom right, and you compare with the observed ones on the bottom left, these are actually on different color bars, but we get an increase of about 0.1 in these simulations, which compares favorably with what we're seeing in reality in terms of the aerosol optical depth. Okay, so in terms of the climate response, these are time series of mean annual temperature for the globe on the left and for the Arctic region on the right. In black and gray is the CSM2 large ensemble. In red are these new members. And you can see that we get a reduction in global warming of about 12%, but this reduction is basically focused north of 40 degrees north, and it's particularly strong in the Arctic region, where we get a 38% reduction in warming rates over this period. Looking at the spatial trends and the annual temperature trends, the middle panel is the well-known sort of pattern of warming, of global warming in the CSM2 large ensemble with quite strong Arctic amplification. On the left panel are the trends in this new ensemble, and you can see that we're still getting warming, but it's quite a bit less strong. And then the panel on the right shows the differences, right? So we get this cooling that's particularly strong over the Arctic Ocean, and then over the northern continents and over the North Pacific. Over the southern hemisphere, there's no change in temperature trends. There's a very interesting seasonal kind of pattern. Now, these aerosols are all going in the summer, and they're short-lived because they're mostly tropospheric, so you might think that we might only be impacting summer temperatures. But here I show the difference in the temperature trends in the summer on the left and in the winter on the right. Now, you can see in the summer that the slowdown in warming is particularly pronounced where you have the fires, so over the northern land masses. But you can see in the winter that the greatest slowdown or relative cooling is actually over Arctic sea ice. And what happens is that you have a delayed response. In the summer, you melt less sea ice when you have this increase in fires. You end up the summer with thicker ice. That thicker ice lasts into winter, and the thicker ice in the winter then gives you the colder temperatures over the Arctic Ocean. We do see global changes in precipitation too, and we see a tropical shift in precipitation. And this is mostly due to the fact that we're slowing down the warming in the northern hemisphere, but not in the southern hemisphere. So we have this kind of hemispheric temperature gradient response. So this is consistent. This is work that's been around for 20 years. And then we also see, a reduction in precipitation in the Arctic. And this is probably just because a warmer Arctic is a wetter Arctic. So if your Arctic warms slower, then it also, the precipitation increase is also slower, right? So you can see the zonal mean precipitation differences on the right there. Sea ice extent. On the left, I show the annual mean Arctic sea ice extent. On the right, the September. Again, like the previous time series, in black is the CSM2 large ensemble. The bold is the ensemble mean. The black are the gray are the individual members. And in red is our new ensemble, right? So we get a slowdown in the rate of Arctic sea ice loss, which is especially noticeable by the end of summer. So you can see that in the CSM2 large ensemble, we pretty much lose all perennial sea ice. So your September sea ice extent goes close to zero by 2060, but in these new runs, we still have about 2 million square kilometers. So there's a delay in the data at which the Arctic becomes sea ice free. So why does this all happen in the simulations? On the left, I show the aerosol concentration number difference. So you can see the biggest differences between 56 and 70 north, which is where we're putting in these enhanced emissions from the fires. And they're going in at the surface, but you can see how they expand or affect both in the vertical and meridionally, north and south. And then on the right, I show the cloud optical depth difference, right? So there's an increase in the cloud optical depth differences. So this is through the aerosol cloud interactions where we're making the clouds brighter. And in some regions, we also increase in low cloud fraction. So these are the spatial mean maps of the annual mean differences in the cloud droplet number on the left. And you can see again, there's sort of the centers of action over Siberia and Canada, but advecting over northern latitudes. For the low cloud difference, we see sort of in some regions over the ocean basins, we do actually see an increase in the low cloud fraction. But over the northern continents and over the Arctic Ocean, we don't actually see a difference in the fraction, in the abundance of low clouds. But what we do see is that the low clouds there are just brighter. So you get a reduction in the net solar flux to the surface on the right panel. With that, I will just summarize that we've seen in observations this like really rapid increase in boreal fires that has been tied to warmer summers and less snow in the spring, among other factors. So we don't really expect this to be a short-term blip, but probably to remain at quite high fire levels, at least in the near future. And this was not taken into account in CMIP6. So there's been this big divergence, and when you do run or rerun CSM2 with this increase in boreal fires, we get some pretty big climate impacts. Boreal emissions matter, and I really hope that CMIP7 just doesn't repeat the CMIP6 scenarios, which were also the same in CMIP5. And this paper, or this work was published last week, so if you're more interested, there's a reference, or you can come and find me. And thanks for your time.
Thank you, Ed. Eventually, I would think that we just don't have any more fire or forests to burn, but I don't know when that happens. So.
Yeah, so that's like what they call the negative fuel availability feedback, and that's why we didn't want to go too far in time in our simulations. I will say that the boreal forest that hasn't burnt yet has increased, probably because of the fertilization effect. Mike Wallace, a colleague of mine in my department, has kind of been doing work on this. So if you actually add the amount of vegetation in boreal region, it's actually been flat, which is quite interesting. But I don't want to speak more to that because it's not my work. But yeah, this would be clearly, at some point, you get rid of the forest, which it's not really a nice scenario to think about. But I also want to say that, so that time series I showed to 23, 24 was the second highest on record in Canada, and 25, you might have seen in the news, has already started a really bad fire season in Canada. And some of these fires have actually survived in the winter in the roots. They call them the zombie fires. And I don't think fire ecologists understand them too well, but it's scary. Or like, I don't think this sort of issue is going away.
All right, are there other questions? See one in the back.
Yeah, did you try and estimate the equivalent CO2 emissions that would come from such a fire thing and compare the warming due to that to the cooling from the aerosol?
So we very much did a back of the envelope, and it's about 3 ppm by 2060. So it's about 6 to 9 months worth of, like in terms of the amount of CO2 concentration you'd have in 2060, you'd reach that level by March of 2059. So it's a very small impact.
Hey Ed, nice talk. Do you know if the sensitivity or this whole mechanism is of similar strength in other climate models, or where does CSM fall?
That's an excellent question. That's following work. So I wish I'd added a slide there so that if you have a friend or access to a different GCM, please contact me. So we're trying to do that with other GCMs. So far, I have colleagues in Barcelona at BSc that have done this with EC-Earth, EC-Earth VEG, or EC-Earth 3/VEG, I believe. They get an even bigger response, so even more relative cooling. I have colleagues in Toronto, Paul Kushner's group. We want to do this with CANI-SM, and also we're trying to do this with E3SM with Haruki, who might be here. But yeah, if you, that's exactly something we want to do because, CSM2 might be quite sensitive to this, but I'm trying to do like an informal MIP for this.
Hey, Ed. So the past few years, there's this huge variability.
Yeah.
Should we expect that to keep going? Is it important, and should that be factored into a scenario?
Yeah, that's a great question. So when we created our scenario, we didn't add any internal variability, a little bit so that we could compare cleanly with the CMIP 6 21st century, which also has no internal variability, but Patricia de Rapentini's work showed how important that internal variability could be. But the interesting thing is that even if you do get, I'll go back to this time series. Even if there is quite a bit of internal variability in recent years, no single year has been as low. Like, we don't seem to have any more low years with no fires. Say, like, the late 2000s, like 2007, I think that is, right? So we actually created a synthetic time series in response to one of our reviewers. On this dash blue time series, we created a synthetic time series where we added white noise with the amount of variability that's the same as the observed variability in triangle. And just because the mean that scenario increases so much is that you don't ever have low fire years. But it's an interesting question. We also want to do runs where we do just create synthetic future internal variability.
All right. So that concludes this polar BGC coordinated session. There will be a polar specific session this afternoon, but thank you all for coming, and thanks to all the speakers. I learned about a lot of really cool new stuff. So let's give them all a hand again. All right. I expect people might be trickling in after lunch. But in case you don't know me, I'm Alice Duvivier. I'm the NCAR co-chair of the Polar Climate Working Group. And then we have two external co-chairs right now. So one is Ed. Can you stand up, Ed? He's very tall. You'll see him regardless. So Ed is just coming on as the external co-chair. He's at the University of Washington. And then Hansi Singh, who gave one of the plenaries yesterday, is the other Polar Climate Working Group co-chair. She's rotating off pretty soon, and she may come in, but she's not in here right now. So I'm going to go ahead and have us get started. I just want to let you know, so each person has about 12 minutes to give their presentation and then a few minutes for and our first presenter is Ching, and she's going to talk to us about clouds and the Southern Ocean.
Thanks, Alice. It's great to be here to be the first talk today. So the talk today is about observation-oriented cloud condensation nuclei, CCN modification over the Southern Ocean using the CAM6. I'd like to acknowledge all my co-authors. So a quick introduction, why do I care about the Southern Ocean clouds? For those of you who tune the model to see the global radiation, you know how sensitive the Southern Ocean clouds can be. However, they are very poorly understood for the reason that we have a limited available observation in history. Thus, most of the model parameterization are North Hemisphere oriented. As an example, you can see the figure on the right. It shows the bias of surface incoming shortwave radiation between the mean of CMIP6 model and the counterpart from satellite project during the austral summer. A large area of red color here essentially is saying the overestimation of the surface incoming shortwave radiation. Given we have the fair amount of radiation at TOA, scientists would hypothesize that this overestimating of surface shortwave radiation might be related to the clouds not being reflective enough over the Southern Ocean. Therefore, we are talking about the simulated entire clouds being not bright enough. From the observation perspective, JMACE 2021 published this paper talking about this natural marine cloud brightening scenario over the austral summertime. It shows the seasonal cycle of cloud droplet number concentration ND along the marginalized ice zone. This is discussed to be related to the seasonal increases of cloud condensation nuclei CCN because of the biological activity. Then, how is the CCN modeled in the CAM6? So quick introduction. Essentially, it's about water vapor condensed on the aerosol. Aerosol are parameterized by type, sea salt, sulfate, secondary organic, primary organic matter, and then by size. Icon mode, accumulation mode, and coarse mode. Accumulation mode AC is the most potential candidate for the CCN. Given we have the reasonable amount of supersaturation here calculated by the balance between the adiabatic cooling and the condensation of water vapor. So given the amount of updraft, and then we calculate the critical radiative of the aerosol, any size larger than that critical radiates can be activated as a nuclei and then falling out to become cloud droplet. At this point, there would be a very fundamental question to ask. So are those Southern Ocean clouds aerosol limited or updraft limited? For those two GCMs, including the UK ESM, the University of Exeter scientists have this study in preparation for published to using those SILBI indexes to quantify the partial variance of the response that can be attributed to the model inputs. As we can see in the figure on the left, it shows most of the tropical area, it's the updraft velocity dominating the clouds here. However, over the Southern Ocean part, as you can see by the arrow, it is the accumulation mode number being the dominant factor in the story over the Southern Ocean. I published a paper in 2024 talking about the latitudinal change of number concentration of accumulation mode AC over the Southern Ocean. As you can see the figure on the right, from Australia to Antarctic, a polar world, we do see the increased amount of total AC in black and the decreased amount of large AC in red, increased amount of small AC in blue. Essentially, we capture this increased amount NCCN over the summer SSO, the South Southern Ocean, based on that the NCCN is more dominant by the number of small AC. So based on the conclusion we have from the observation, the counterparts of the conclusion can be seen or not in the model would be a good question. So Christina and I did this nudged simulation with schemes on the left and the collocation method on the right to check the Southern Ocean clouds over the Southern Ocean, North Southern Ocean, South and South Southern Ocean, and over different regions in different months. So Christina and I published a paper in 2025 talking about this similar figure on the right is the latitudinal change of the NCCN, so separated by size. Here we see, although the icon mode in green and the larger AC in red are fairly simulated, it is the total AC in black, particularly the small AC in blue, that are underestimated. We're evaluating what is causing the underestimation of CCN by the Antarctic coast, and the CCN spectrum on the left shows that most of the time over the NSO, it's the sea salt overestimation causing in this NSO over November, while over the SSO in summer, particularly in February, it is the small sulfate that are underestimated in the CAM6. Then you'll be curious about in nature and by modeling, how is the sulfate and sea salt simulated in the model? By nature, when the wind is blowing over the open water, the wave breaking happens, which is released the film droplets and jet droplets, which can release the sea spray aerosol into the air, which contribute to the CCN and also the ice nucleating particles, INP. In this study, I reduced the sensitivity of sea salt emission flux from the 10-meter horizontal wind speed to its 3.4 to its 2.8, based on those publications using the very recent in situ observation in the summer of over the Southern Ocean. While for the sulfate, the things can be more complicated because of the involvement of chemistry, but long time in short, the DMS, dimethyl sulfide released from the open water, are transferred and oxidized into SO2 and eventually to sulfate, which can contribute to the potential sulfate CCN in the future. In this study, I did sensitivity test about double, triple, and times 10 of the DMS fluxes as a surface emission to see the sensitivity of the CCN. Okay, now we're going into the results of the study. What are the models show after turning down the sea salt emission scheme over the Southern Ocean? As you can see, I plotted the scatter plot of simulation on the Y and observation on the X, colored by the latitude. As you can see from the control run on the left and the wind up speed updated run on the right, the CCN over 44 and 50, between 44 and 55 are largely improved because it's more close to the diagonal line here, while those blue dots representing the CCN over south of 55 are not largely improved, potentially caused by this potential sulfate over this area. As a quite typical case for sea salt, in this early spring 2017, I plotted the time series of the base run of observation in orange, base run in blue, base run on the top, update of sulfate in the middle, update of sea salt in the bottom. It can be seen that from here and here, the overestimation of CCN are solved after we tuning down the sea salt. This is also confirmed by seeing the chemical composition, including the mass concentration and number concentration as a function of latitude. I plotted the base run on the left and the modification, including both turning up sulfate and turning down sea salt in the middle. As you can see, after this change, the chemical composition has largely been changed after the simulation, after the observation-oriented simulation, which on the right corresponds well with the 0.5% and 0.2% supercharge saturation. Similar case, however, this is based on the sulfate, which happened in the very deep summer. In 2018, from Mawson to Hobart, the model underestimated those peaks here, here, and here, which got further underestimated when we tuning down the sea salt. It has to be by doubling, tripling of the DMS when you see in the middle that the peaks are well captured by the model. So the DMS tripling method is largely improved the NCCN performance here. Again, I checked the chemical composition. As you can see, the updates really changed the chemical composition a lot by changing the aerosol type from chloride-based to sulfur-based. Take-home message here, for the reason that this field camping markets measurements of aerosol radiation and clouds over the Southern Ocean covers a longer time duration and a larger area, which provides a great data set to not only look at the sea salt scenario, but also the sulfate scenario in different time over different region. Both modifications improve the CCN over the Southern Ocean. And the take-home message of the two sensitivity tests would be sea salt emission power law can be regional dependent. This can also be related to the wave, except the wind speed over the open water. And then the low bias of NCCN in the summertime over the SSL can be related to the lack of sulfur. No matter what is the right sulfur in the real atmosphere that scientists talking about a lot in the bottom part of this slides, it has very different complicated chemical composition that scientists hypothesis to be the real sulfur in the atmosphere. The CAM6 is just lacking of the sources of the S here. However, I'm not going to talk about so much complex of chemistry here. Instead, I would go through a different path, which is to look at how does this change between the ratio between sea salt and sulfate would be changed by a lifetime of accumulation mode error also, which is also influenced by the synoptic updraft and down descent because of the close by region of the storm track, and eventually looking at its influencing on the Southern Ocean clouds. I would like to acknowledge my collaborators, including NASA from PNNL, who is doing the similar type of job, but on E3SM. I'd like to acknowledge Jack Chen, who showed me his script when I first visited NCAR, also Simon and Chuda, one from ACOM, from rail, from telecommunication, and offer suggestions and feedbacks. Yun Qianzhu from NOAA CSL providing instructions on the simulation, and people including Jesse, Isla, Cecil, Brian, who always have an open door policy to me no matter when and no matter what question that I asked. Those are the institutions and funding agencies that is helpful for this research, including University of Oklahoma, NSF, NCAR, and DOE. I would stop here for any questions and comments. Thank you so much.
But okay, there we go. So thank you so much. We have time for a couple questions. Anyone here?
Nice talk, Ching. I'm not doing aerosol things, but I just want to understand what is the implication of the microphysical parameterization improvement in current Chem6 model from your research?
So currently, this research is not reaching as far as microphysical perspective on this influencing on clouds. This is based on cloud condensation nuclei perspective, saying not considering the updraft or the dynamic factors influencing on the clouds. What if the background aerosol loading is different after changing from the base run to the update on both sea salt and sulfates? So I think the implication for microphysical perspective essentially is going to be, if we changed and improved the performance of NCCN, would that first of all change the ND in clouds, particularly the low clouds over the Southern Ocean when supercooled liquid water are regarded as a top first priority in this scenario? And then the second thing would be how would the lifetime be changed, because we also change the lifetime of CCN over this area. Being a very pristine region for Southern Ocean clouds, exactly the next step to go is to start thinking about the microphysics part from CCN to clouds, like aerosol clouds interaction. Yep.
All right, do we have any other questions? I guess I have a quick question. There were a lot of headlines this week about penguin poop being a source of CCN, and I assume that's probably through like ammonia and nitrates or something, but we have in more seriousness, we're probably not adding penguins to CESM anytime soon. But I do think coupling the biogeochemistry, especially in the marine system and in sea ice, as a source to the atmosphere would be really beneficial. So thank you so much for this.
Thank you so much. I also mentioned this fully coupled potential of ocean and atmosphere and chemistry and also biology would be super helpful in this story.
Yeah.
Thanks, Alice.
Thank you. All right, so we're going to move on to our next speaker. We have Chloe, who is going to be talking to us about atmospheric responses to Antarctic sea ice.
Yeah, so thanks for having me. I'm Chloe, I'm a grad student at CSU, and I'm gonna be talking about some work I've been doing with my advisor, Dave Thompson, and then also in collaboration with Ed Blanchard-Wigglesworth at the University of Washington, as Al said, talking about the local atmospheric response to especially some of this recent Antarctic sea ice loss. So I'm sure all of you are very aware of this time series, which is of Antarctic sea ice across the observational period, where prior to 2015, there was a slight positive trend, and then since then, in the last decade, there's been really rapid change and lots of variability. And there's been quite a lot of work done trying to understand the causes of this variability and the reasons behind this big shift in the behavior of Antarctic sea ice, but there's been less work done on trying to maybe understand the potential implications of this Antarctic sea ice loss. There's been a couple studies I'll highlight here. One from England et al. In 2018 that was a modeling study looking at this particular figure is looking at the response of the jet and zonal winds from Antarctic sea ice loss, and then a recent paper from Simon Josie in 2024 that was an observational study that was looking at, in this particular figure, the change in storminess from a decrease in sea ice loss in 2023. And so we were looking to kind of extend on this work, and in particular, look at maybe could we start to use some of this observationally constrained data to explore the impacts of Antarctic sea ice loss, but recognizing that there's obviously biases associated with said data, and so how does it compare to some modeled impacts as well. So for the observationally constrained data I'm going to use, so it's monthly data, monthly gridded data, sea ice data from the NSIDC, a bunch of atmospheric data from ERA 5, and some cloud fraction data from CERES. All this data covers the period from 1979 until this past September. And then for the model data I'm going to use, so I'm using PMIP experiments, or PMIP style experiments with CESM2. So if you don't know, these are atmosphere-only time slice experiments. They all have 100 ensemble members. The experiments are run for 14 months. The first 2 months are discarded, so you end up with 12 months of data, and they're forced with the particular experiments I'm using is one's forced with present-day SSTs and a future Antarctic sea ice state, and ones with present-day SSTs with a pre-industrial Antarctic sea ice state. So basically, if you take the difference between those two experiments, you can isolate the impact of just a change in Antarctic sea ice state on the atmosphere. So this gives you a more direct kind of ability to see just the implications of Antarctic sea ice change or loss in this case. So for the observational results, so I'm using kind of this local regression methodology, which is simply a grid point by grid point regression analysis, where, for example, this map here is a regression of turbulent heat flux at each grid point onto sea ice loss at each grid point, which is just inverted sea ice. I just do it onto sea ice loss just because we're interested in what the change in turbulent heat flux in this case is based on a decrease in sea ice. So the way you do that is, for example, that little black box there is, for example, a grid point, and you take the turbulent heat flux at that grid point and regress it onto the standardized value of sea ice loss at that grid point. So the regression results, every single grid point is treated individually. So this allows you to kind of, you can look at each grid point treated individually, and so maybe it can build some confidence into your results, but it also allows you to kind of explore the regionality of these relationships and see how maybe different areas are affecting different aspects of the atmosphere differently. So for this case, you see that quite generally there's an increase in turbulent heat flux due to sea ice loss. That's not particularly surprising, that's been shown before, and this is, of course, this is from data that's across the whole time period, across all months, but there is a notable seasonality associated with this particular relationship. So now I'm showing regression results, the same grid point by grid point regressions, but this time broken up by season. So each column is a different season. I've listed the months at the top, and then at the very top, this is sea ice concentration onto itself. This is just to kind of give you an idea of where the largest variability in sea ice is, just to kind of have maybe a picture in your mind of where the largest variability in sea ice is spatially. And then on the bottom is turbulent heat flux regressed onto sea ice at each particular grid point, this time broken up by season. So you can see this big seasonality where you're getting the largest response in the winter and the smallest in the summer. And you can understand the seasonality just by simply a temperature difference being between the ocean and the atmosphere being largest in the winter and smaller in the summer. Now the turbulent heat flux for the rest of this talk, I guess I'm going to focus primarily on just August, September, and October, and that's mainly just because otherwise you end up with a lot of panels and it's a lot of figures to look at, but I'm happy to show the other months if anyone's interested. So we can look at, beside turbulent heat flux, we can look at other atmospheric variables of interest. So in this case, we're looking at turbulent heat flux on the left, then 850 vertical velocity, precipitation, and then cloud fraction all the way on the right. And these are the same grid point by grid point regressions onto sea ice, loss of sea ice. And so you see that in addition to an increase in turbulent heat flux going from the ocean into the atmosphere, you also see areas where there's an increase in vertical velocity, an increase in precipitation, and an increase in cloud fraction. Now, all four of these kind of responding in this way is not particularly surprising. They should kind of respond similarly, because if you have an increase in turbulent heat flux, you'd expect maybe from that heating there'd be more vertical motion and more precipitation and cloud fraction as a result. However, I think there's some interesting regionalities, especially with Omega, where particularly East Antarctica and around the Antarctic Peninsula pop out as having a larger response than other regions, versus the variables like precipitation and cloud fraction have a more uniform response. And now, since these are only for one particular level, we wanted to look at, does this response actually extend higher into the atmosphere? And so these regressions are, so the panel on the left is Omega at 500 and 850, and then on the right, that panel is temperature response now at 500, 850, and 2-meter temperature. And so the main takeaway from this is that based on these local regressions, your response is not isolated to the low levels of the atmosphere near the surface, but you're actually getting a response in vertical velocity and temperature that actually extends higher up into the free troposphere, which maybe has potential implications for maybe larger scale circulation. And so this is just, so that was just the observational results based on this local regressions, but as I mentioned, we wanted to kind of look at how those compare to now the modeled simulations. And so again, we're using two experiments, one with a future Antarctic sea ice state, which is less sea ice, and one with a pre-industrial sea ice state, which is more sea ice, and we're taking the difference between those. And so this figure here is just simply the difference in sea ice between these two experiments, just to kind of show you again, you're having a reduction in sea ice in the future sea ice run, and that it's kind of similar areas of where you saw that large sea ice variability in the observational data. And so we can look at similar variables in the models. So now we look at the response, or the difference in turbulent heat flux, 850 vertical velocity, precipitation, and cloud fraction. And again, this is the difference between these two experiments, so I think that's important. Obviously, the observational data was a regression, so you can't quite compare these apples to apples, but I think you can start to qualitatively compare these results from what we're seeing with the observations, which is that given a decrease in sea ice in these PMIP-style experiments, you're getting an increase in turbulent heat flux, an increase in precipitation, and an increase in cloud fraction. The 850 Omega results are definitely a little messier and a little more, it's not as clean or not as similar to the regression analysis, which is interesting. And we can kind of start to compare these results with the observations a bit more by kind of saying, so for the observational results, the regressions were all per standard deviation of sea ice, which works out to about 20 to 25% decrease in sea ice. These PMIP experiments, the change in sea ice between the two simulations was about 35 to 40%. So if you kind of start to say generally, okay, given those two amounts of decrease in sea ice, what's roughly the amount of increase of turbulent heat flux, precipitation, and cloud fraction compared between these two results? And what kind of is what I want you to point your eye to is that there is an increase in the amount of turbulent heat flux increased in the PMIP results and precipitation and cloud fraction, but it's only a little bit of a change. And given that there is a more reduction in sea ice in the PMIP experiments, again, you can start to maybe see that there actually are kind of comparable results, which I think is quite interesting. And then finally, so again, we looked at different vertical levels in the observations, so it's worthwhile to obviously do this in the model results as well. This is quite a different picture than what we saw in the regression analysis. So this is temperature on the left at 500 and 850, and then Omega on the right at 500 and 850. And temperature, there's very little response at 500 versus there's quite a similar response at 850. Omega is, again, a little bit messier. There's definitely a little bit of a response, but it also dampens quite a bit as you move up to 500. And so I guess generally, if you think about, comparing these with the observational regression results, that the observational results show that there's more of an impact higher into the troposphere than these results from the model do. So this work is very much kind of still in progress, but some of these key points so far we've been thinking about is that I think based on this local regression analysis, we can use this observationally constrained data to try to start to explore these impacts. The results can be kind of qualitatively compared to this PMIP experiments, and I think they are actually relatively similar. And then a kind of very notable difference between the two results is that the results from the observations show impacts much higher into the atmosphere than you're getting from the PMIP experiments. So my contact information. Happy to take any questions. Thanks.
All right. Do we have any questions for Chloe?
Very nice talk. Learned a lot. So I just have a question about the asymmetry of your cloud fraction and precipitation response to the loss of Antarctic sea ice. It seems like to the eastern side of the Antarctica, the response is actually the strongest. Is that just because of the change in surface heat fluxes?
Are you talking about, sorry, the change in these results?
Yes.
Yeah. So it is interesting that, there's notable areas, where you're getting a much larger response. And I think that is due to because if you look at the temperature profile of the PMIP results, that's where you're getting the most heating. So I do think that's why those two areas pop up, because you're getting the most temperature response in those areas that I think are resulting in more turbulent heat flux and more precipitation. But it is notable that those areas pop out more, or those areas pop out as kind of hot spots in these that maybe in the grid point by grid point regressions, it's a little bit of a more uniform response, which is interesting.
All right. Any other questions? No? All right. Thank you, Chloe. Before we transition, I just wanted to say that Hansi, our other co-chair, is in the room now. So will you stand up and wave to people real quick, Hansi? So Hansi's been serving since 2020, and she's going to rotate off in February, but we have the three of us for a couple months so that we can have some transition between things. But feel free to reach out to me, Hansi, or Ed if you have any questions or anything. So yeah, I just wanted to make sure that everyone saw her talk yesterday, so you might have already known who she was. All right, our next speaker is Molly, and she's going to talk to us a little bit more about constraining sea ice thickness with satellites.
Thanks, Alice. Hi, everyone. My name is Molly. I'm currently an NSF, currently an ASP postdoc here at NCAR. But I'm going to speak to you today about some work from my PhD at the University of Washington, and really quickly want to shout out that a lot of this work was guided and supported by my advisor, CC Bits, and then the folks at the Data Assimilation Research section here at NCAR. A lot of what I'm going to present today is a survey of results from a project at the end of my PhD, which was attempting to constrain sea ice thickness estimates globally using the SICE sea ice model. I've left out a lot of the details, especially as they pertain to the data assimilation side of things. If that's interesting to you, please come find me afterwards and we can definitely chat about it. But for the sake of time, a lot of that stuff is not explicitly in here. So, motivationally, the source of this project really came from the fact that we have biases in our sea ice models relative to observations, which I hope is not news to anyone in this room. But our models are often really important sources of spatiotemporally complete information, particularly when it comes to things that are difficult to observe. So we want to be able to both accurately use those models and then also improve them. And I'm kind of illustrating one front-facing version of model bias in the sea ice model by showing you here on the right an ensemble mean from a 30-member size 6 set of simulations that's forced by a data atmosphere and has been tuned to a less melt scenario in terms of the kind of annual average sea ice thickness in that set of simulations. And then I'm comparing it on the left to a recent observational estimate of sea ice thickness over a similar time period that's been estimated from the Cryosat-2 radar altimetry observations. And you can see that not only does our model tend to kind of overestimate sea ice thickness in many parts of the Northern Hemisphere, it also exhibits a different spatial distribution of thickness than the observations would otherwise indicate. And if we turn and look at the Southern Hemisphere, these differences are kind of even more pronounced. I will note that this validation product that I'm using on the left is similar in the sense that it is based on Cryosat-2 radar altimetry observations, but it's, as far as I can tell, currently the only thing of its kind that does a kind of gridded monthly estimate of sea ice thickness in the Southern Hemisphere. And in that publication, they do note that they tend to kind of have thicker estimates of sea ice across most of the Antarctic compared to other observational products, and they can't really say why that is. Maybe it is that the ice is thicker, maybe it's an error with their methodology, but if we compare these two things, you can see that there's quite a bit of difference, such that in absentia of other kind of validation information, it's hard to place confidence in either one of these sources of information. And when we get to that point, one approach that you can take to kind of reconcile differences between models and your observational estimates, or try to understand why they are so different, is to assimilate the limited observations that you have into the model. And this has been done fairly commonly now, I would say, actually, in sea ice models, where the two most commonly assimilated types of observations are sea ice thickness and sea ice concentration. And those two things have pros and cons in terms of their utility for this application. For sea ice thickness, we do have some available observations, but if they are temporally available over long periods of time, they're often very spatially limited. So thinking like in situ buoy moorings, for example. Whereas if they're more spatially available, thinking from remote sensing, then they often have much shorter temporal range. This is a bit of a bummer, given that more idealized studies have illustrated that assimilating thickness observations does actually improve our estimates of the sea ice state, both in terms of thickness and concentration. And then on the other bucket, sea ice concentration observations have the good fortune to be part of a much longer, temporally high resolution and spatially continuous record. And they're available in forms that make it easier to work with. But studies have also demonstrated that while they do an okay job correcting model biases for sea ice concentration, particularly near the ice edge, they can have negative impacts on sea ice thickness estimates in models, particularly in perennially ice-covered regions of the Arctic. Our project wants to make a case that we should think about assimilating a third type of observation, which is sea ice freeboard, which, if you're not familiar, is a measurement of the height of the ice surface off the height of the sea surface. It's typically a little more readily available than sea ice thickness observations, and in fact, many of our remotely sensed thickness products are estimated from the freeboard products, from the same missions. And freeboard is available from recent satellite missions, including Cryosat-2, which targets the snow-ice interface using radar altimetry, and ICESat-2, which targets the snow and ice top of surface using laser altimetry. And our kind of main motivation for this is that it hasn't been commonly done yet, which is a bummer because the observations are typically more widely available than thickness observations, and they tend to have lower estimates of uncertainty, which becomes important in the data assimilation process itself. And in particular, if we think about the ICESat-2 freeboard observations, they are available at a really unprecedented density, though only from late 2018 onward. So this figure is illustrating the number of observations in millions for freeboard that are available from ICESat-2 for the Arctic in teal and the Antarctic in purple over the beginning of the ICESat-2 collection record from late 2018 through 2020. The solid lines represent the 30-day running mean, and the shading represents the total observational count. So you can see over this time period, on any given day, you're talking between 1 million to tens of millions of observations, depending on which hemisphere you're looking at. And this is actually, in fact, too many observations to assimilate directly into the model, given that at a nominal 1 degree resolution, you're talking about a model grid cell seeing anywhere between hundreds to thousands of individual observations, which actually tends to pollute the data assimilation analysis. But we can still make use of the majority of this information by aggregating it onto the model grid, which allows us to represent freeboard in each grid cell as a distribution. And from that, we can extract a representative observational value and more accurately constrain various sources of observational uncertainty with that grid cell level observation, which winds up generating an along track gridded freeboard product or data set that we think is potentially quite useful from the perspective of trying to constrain a sea ice model. So in another world, this would be a video that would very gently expand and contract with the sea ice cover to show you where there are freeboard observations in each hemisphere. But for now, I hope this is enough to convince you that we get pretty good coverage from this kind of reduced product in both the northern hemisphere and the southern hemisphere. So with this product, we can start to think about taking it and assimilating it into the CES6 model. And we do that in an ensemble data assimilation framework using the data assimilation research testbed that's maintained at NCAR. And by doing so, we can start to think about answering questions particularly related to whether or not we're going to be successful in constraining our estimates of sea ice thickness when we use these observations in this manner. And when we do so, what does that tell us about our model? This presentation is really targeted at the first question, which is mostly that a lot of the results from the initial attempts to do this have teed up ways that we can think about the second question, but not really conclusively given us a lot to work with there. So we're mostly thinking about, does this work in terms of constraining sea ice thickness? So to do so, we're going to assimilate our product of daily along-track gridded freeboard estimates into an ensemble of CES6 simulations. And we're going to validate against a number of different products for both sea ice thickness and snow, which will become important later on. I'm going to note that what I show for validation products are monthly gridded estimates of sea ice thickness. It's difficult to validate daily data at a spatially comprehensive manner. If you're interested in that, there are some buoy comparisons I can show you later. But our first step is to compare the assimilation impact on the model's estimates of freeboard. So here I'm showing you the % mean absolute error reduction compared to an unconstrained model ensemble mean when we use a particular thickness validation product, or freeboard validation product, which is the ATL20 available from NASA. And what you should point out, or what you should focus on here, is that blue colors indicate that we're reducing the error in our model by assimilating these observations. Red colors indicate that we're increasing the error in our model by doing so. And you can see that in both hemispheres, we're doing a pretty good job in terms of reducing the error in our model's freeboard estimates, anywhere between 20 and 80%. So this is a somewhat trivial result. You assimilate, you constrain a model with freeboard observations, you should improve your model's estimate of that observational quantity, but it verifies that our assimilation is working in the way that we intend it to. That picture gets a little more complicated if we then move out of the observational space and think about how these observations have influenced the unobserved parts of our model, including sea ice thickness. So here I'm showing you the same metric, but this time I'm using a validation product of monthly sea ice thickness compared to the thickness estimates in our constrained model. And you can see a number of things that kind of immediately jump out. First of which, across most of the Arctic, we're doing a good job reducing error in thickness estimates compared to the validation, which is, again, the blue color. But if we look at the southern hemisphere, we generally appear to have an extremely low efficacy, so not much change in thickness as the result of assimilating these observations. And then in the northern hemisphere, we have this fun little dipole hanging out, in which we appear to improve model estimates kind of in one part of the Beaufort Gyre and degrade the model estimates of thickness in another part. Both of these things are really interesting for the sake of time, and because it's, I think, largely a validation product issue, we're not going to talk much about the southern hemisphere today. If that's interesting to you, again, please come find me afterwards. But we are going to focus on what might be going on in the northern hemisphere. And that, I'm going to argue, is largely due to the relationship between freeboard ice thickness and snow depths, and how they interact with kind of pre-existing model biases. So here I'm showing you annual average sea ice thickness in the validation product on the left, our constrained model estimate in the middle, and the unconstrained model ensemble mean on the right. And I'm highlighting that region where we have the dipole in model improvement versus degradation. I'm going to use a little visual aid to block out the bottom 2/3 of this region, and we'll point out that here the validation and the constrained thicknesses look pretty similar, which makes sense that this is a region where we're improving our model estimates by assimilating freeboard observations. But if we look at the other side of this region, it's actually the validation and the unconstrained model that look most similar, largely due to the fact that the assimilation appears to have thinned ice in the constrained estimate in this region. Which is a kind of what the heck moment. Why would they do that, especially given that the validation data and the model already kind of agree in this region? And that, I think, has a lot to do with how we represent freeboard in our data assimilation framework and how that influences snow estimates in the model. So remember that we're assimilating ISAT2 freeboards, which target the top of the snow and ice surface. So snow depth is kind of implicit in these observations, and they're used to update snow depth as well as ice thickness in the model. So the validation product that we're using for snow depth is on the left, again in the annual mean. The constrained model estimate for snow depth is in the middle, and the unconstrained estimate's on the right. And we'll just note in general that the snow depth magnitude in regions where we have the most snow is larger than both the validation or the constrained model. And that's particularly true if we highlight again that region that we were interested in that had kind of unexpected model degradation. We can target this a little more specifically by looking at biases. So if we actually calculate the bias in snow depth and ice thickness compared to validation products, this is what we wind up finding. So on the left is the difference between the validation product and the constrained model estimates of snow depth, where you can see red colors indicate we're overestimating snow depth in our model estimates, and blue indicate that we're underestimating snow depth. And then on the right are two versions using two different validation products of that same calculation for ice thickness. And the main thing that I want to highlight here is that there's a really tight spatial overlap between where our constrained model is overestimating snow, it underestimates ice thickness. There are a couple potential reasons for this. I think the most prominent one is that the way we represent freeboard as a modeled quantity, calculating it from snow depth and ice thickness in the model, is a combination, like a weighted combination of snow depth and ice thickness, weighted by their relative densities, which we assume to be constant. That equation tends to more tightly relate snow depth to the freeboard value than ice thickness to the freeboard value. There's also a potential that the length scales of sea ice thickness in the model tend to kind of overly aggressively smooth the sea ice thickness analysis, especially because we have such a dense observational network, and we're allowing those observations to influence a lot of the Arctic when we assimilate them. So there are potentially multiple contributing factors, and I don't have a nice neat bow on this story to tell you exactly what's going on. But snow is a really important plot element in my mind, and I'm excited to maybe get to update the story with some simulations that are running now on the newly reinstated derecho. So more on that later. And with that, I think I'll wrap up and just generally give kind of a summary of the current status of this project, which is that we find that these freeboards tend to improve our estimates of freeboard, and then also across most of the Northern Hemisphere, snow depth and ice thickness, with some exceptions. Things I didn't show are that this also improves model estimates of total sea ice volume in the Northern Hemisphere, though it has a more complicated impact on sea ice cover. Secondarily, as currently represented, we're going to acknowledge that these freeboard observations may have some limitations, especially given the way we represent freeboard in the model, when constraining both ice and snow at the same time in the Northern Hemisphere. And we currently have an ongoing experiment that's looking at just updating thickness without updating snow to see if that's potentially more effective. The thing I didn't talk about at all, but which shouldn't be surprising to anyone, is that validation in the Southern Hemisphere is really hard, and it's going to require a little bit of extra legwork. If you're excited about this or you know of any products that I don't know about yet, please let me know. And then, oh, that should be a 3. That's fun. But then the other directions that we're thinking about investigating a little more deeply, in addition to this snow question, is how our assimilation configuration choices and the specific observational network of ISAT2 potentially influence this analysis. So with that, I'll stop. I'm assuming that I went over time a little bit, but I'll take any questions.
All right. Thank you so much. I think we have time for one question. Anyone?
Just a detail, which thermodynamics are you using? The bits and Lipscomb or the new mushy layer? So K-therm 1 or 2?
I'm pretty sure it's the mushy layer.
Okay, because I'm wondering if there's just feedbacks in the data assimilation and then the thermodynamics that are really influencing the freeboard. Might be interesting to try the bits and Lipscomb.
Yeah, that's a great point, Dave, especially in the context of how things operate in the summer, where we tend to kind of drastically reduce sea ice more than we should. I'll take a look at that.
The only other thing I was going to say is I believe Sarah Cassini is working on a product in Antarctica. It might only be some seasons, so but you might want to reach out to her as a possibility.
Great. So thanks, Alice.
All right. So our next presenter is remote. Is Alec online? We're going to hear a little bit more about ISAT2.
Awesome. Oh, I'm sharing my screen, right? Or are you?
We were expecting you to share yours.
Yeah. Okay. You see that okay?
Yes.
You can hear me okay?
Yep.
All right. Great. Well, thank you very much for letting me give this talk remotely. I really appreciate it. Yeah, today I'm going to be talking about our efforts to constrain CI simulations with ISAT2 altimetry data. So a nice follow-on to Molly's presentation. We're kind of halfway through this project, funded by the NASA ISAT2 science team. Big shout out to my colleagues Chris and Maddie, who are working with me on this project. Chris especially has produced basically every plot I'll be showing today. So I'm going to be talking mostly about that project, and I've got a few slides at the end referencing a newer project we have starting up about sea ice melt as well. And I gave a similar talk with a lot more background at the winter meeting. So kind of similar to what Molly said, I'm going to be skipping over a lot of the kind of methodological details. Apologies, but I think it's justified, and hopefully there's a decent amount of people in the room that saw that earlier presentation. There we go. Yeah, so we're kind of inspired by trying to think, looking at maps like this of sea ice conditions and trying to think how we can better use the altimetry record to constrain CMIP6 results. The kind of traditional method to date has been to use passive microwave concentration data to assess sea ice output. Passive microwave CF concentrations are shown at the bottom for the Arctic on the left and the Southern Ocean on the right. That makes sense. It's a really nice data set. It's a 40+ year record of quasi-daily information. It's really nice to use. You can look at trends. You can look at variability. The problem with it is that it doesn't give us a huge amount of information within the pack ice. So if we look at the Arctic in winter, there's a lot of white. So we just have a lot of fully concentrated ice and not a huge amount of information. Above the concentration, we start to see information we can obtain from ISAT2. So as Molly said, what we measure with ISAT2 is freeboard, the extension of both sea ice and snow above sea level. Those freeboard results for the Arctic on the left in green, and then for the Southern Ocean on right. And then again, similarly, we can also derive quantity of sea ice thickness from that freeboard. We're a little bit more confident about doing that for the winter Arctic, where we have better information about snow loading. And so if you look at these maps, you just kind of eyeball them, you can just start to see a lot more information, spatial information within those maps, within the consolidated ice pack. And that's the kind of information we want to better leverage for assessing sea ice models. The big downside and the big caveat of doing this is we have a much, much shorter record. So we've got about 6 going on 7 years of ISAT2 data compared to the 40+ year record. So, you know, our hypothesis is that we're getting close to the point in which we can use altimetry to do kind of similar types of constraint. So the two key things we need to consider when we do this kind of work are observational uncertainty and internal variability. ISAT2 is really, really good at measuring freeboard. It's very, very good at doing it, and it's done it virtually uninterrupted since it launched in 2018. So the observational uncertainty of freeboard is low. When we start bringing in additional input assumptions regarding snow loading and ice density, that's when the uncertainty radically increases. Again, I'm not going to go into the details, but we kind of have this summary of our uncertainty estimates on the bottom right there, which is what we use in our plausibility assessments. The other thing we then need to consider is internal variability. And as I said, because we're dealing with this very short window, internal variability is going to be higher than the kind of longer term means we might be getting from the passive microwave data. Our kind of an example estimate of internal variability from CMIP6 for freeboard, and this is the September freeboard, is shown at the bottom left. And unfortunately, there is a kind of a decent amount of internal model variability. But this is kind of similar to what we see with actually the area and thickness results too. So we follow a similar approach to other studies of looking at this for the larger ensembles and taking a multi-model mean. So we put that together and we can produce these kind of plausibility scores that, again, previous studies have presented that we're building on. Again, skipping a bunch of the methodology, there's a bunch of stuff we have to do to actually think a little bit about density, kind of some of the topics that Dave was just mentioning with the thermodynamics, but For now, we're just going to ignore all that and say we can kind of estimate freeboard from the derived outputs of thickness and snow depth. And we can produce plots like this. So this is a plausibility assessment. Here we're showing Arctic Ocean annual means for the ISAT2 period. So all of the total freeboards essentially that we've measured over the Arctic Ocean. The observations are shown by the red point and the vertical line. So it's about 27 centimeters on average if you're interested. Then all of the CMIP6 results are shown below that. So we have the CMIP6 model mean, multi-model mean, and then all the individual models below. Those horizontal lines represent that combined plausibility based on the observational uncertainty and internal variability. Again, for freeboard, the observational uncertainty contribution to this is small, but the internal variability contribution is high. That width is quite big, so that makes it hard to kind of decide whether some of these models are implausible, but you can see towards the lower end of this ranking a bunch of these models that are considered implausible at the kind of 2 or 3 sigma level. Then on the right there, I'm not going to explain that too much, but that's the mean absolute error at kind of a spatial scale. So that's where we start to integrate some of that regional information about freeboards. So we can see this doesn't increase monotonically. So we know that there's some kind of offsetting regional biases that we should consider if we want to be a bit more careful about this type of constraint analysis. Doing the same for the Southern Ocean, we see a kind of much different response, a kind of much worse response, if you will, for the models. So that CMIP6 into multi-model mean is now significantly lower than the observations, whereas for the Arctic, it was miraculously right on top of it. And so there's a lot more models that are considered implausible. And again, this was kind of expected from previous studies that have analyzed sea ice area. We're hoping to add a bit more information about, as I said, the freeboard and thickness using this approach. There's lots of different versions of this plot I could show, but instead we try to kind of summarize it all in this plausibility matrix. So we have this table, and now the x-axis is showing all those different metrics that we're looking at. So we only have thickness for the Arctic. And then the models, we have the CMIP6 multi-model mean at the top, and then below that, the models are all ranked based on their kind of mean plausibility across all of these metrics. I highlight the CSM2 ones because I'm at a CSM meeting, and luckily they're doing quite well. So good job, CSM. This is the CSM2 contribution to CMIP6, and then the CSM2 Wacom models. Yeah, and there's been talk about some of these kind of little scores, like the late summer low sea ice bias. You can kind of see by some of the reds that we're observing in those rows. So there's a bunch of extra work that we did to look at how we can use that constraint. Obviously, the next question is, do we use exclusion? Do we use a weighting to then kind of do something with that plausibility analysis? We looked a little bit at the seasonal cycle in sea ice volume, and then we looked at a little bit more in terms of the regional plausibility ideas as well. So if you do want to learn more about that, we do have a preprint at GMD that goes into much more detail. So that was kind of what we talked about at the winter meeting, a very, very quick version. What we've been doing since then over the last few months is trying to add in some more CSM models. So that's what I want to show you in the next slide or two. So now just showing the same kind of plausibility matrix, but we've added a bunch of extra CSM2 runs in red. So thanks to Dave and Alice for giving us some access to Duracho to be able to access some of those runs. I really appreciate it. So some interesting things we can see here, the CSM2 less melt run, which I think has already been mentioned today, where CSM2 was calibrated to perform better in some of these kind of sea ice assessments, is now at the top. So again, that was somewhat expected because they kind of cheated and calibrated parameters to do so. But yeah, this just gives further evidence that was a successful calibration, if you will. So good job. We have the CSM2 large ensemble below that too. That's again performing decently well, and I'm going to touch a little bit on the difference between that and the CSM2 CMIP6 runs in the following slides. And then we have the kind of CSM development runs that are being generated towards CSM3. So those responses are a little bit mixed, and I think that's going to be touched on more today. The kind of blues in the Southern Ocean are those kind of positive biases in sea ice area that we're seeing as well, but just for a very, very short window. But it's quite mixed. It's not necessarily bad across the board. So yeah, a lot more we can think about, and we have this framework set up to explore even more of these if you guys want to. So as I said, one of the interesting things is kind of the difference between the large ensemble and just the regular CMIP6 contribution. The CMIP6 one was only 3 members, whereas the large ensemble has 50. It's the same forcing, so we were kind of expecting similar behavior, but we do see some kind of differences in worse performance with the large ensemble. And we wanted to look into that a little bit more. So this is just kind of hot off the press analysis that we've done over the last couple of weeks. So thanks again to Chris for really getting this done in time for this meeting. So here what we're showing is the Arctic Ocean area on the left, thickness in the middle, and freeboard on the right, from the CSM2 CMIP6 contributions, the 3 members in red with the multi-model mean in bold, and then the large ensemble in black, for this kind of modern era altimetry period, we'll call it. So yeah, what you can see is, again, this is kind of a different demonstration of the high internal variability, which makes this kind of assessment quite challenging. Again, we try and kind of capture that in our plausibility assessments, but it's hard, especially when we don't have a bunch of very large ensembles. We're struggling a little bit with that. It's interesting that the CSM2 CMIP6 runs in this ISAT2 era. The 3 members all show very high sea ice. Again, it seems to be just driven by internal variability, but that was interesting to note. So we've done a little bit of work of trying to explore that. Sorry if I'm kind of running out of time, but Chris has done some nice work to use bootstrapping, where we try and take 3-member samples from the CSM2 large ensemble to produce a similar looking 3-member mean. You produce histograms shown here. This is an example of where the kind of distributions that we obtain from the large ensemble are consistent with the CSM2 CMIP6 run. Then in some of the other metrics, like the Arctic Ocean sea ice area, they're not consistent. We see a significant difference between the CMIP6 contribution and CSM2 large ensembles. So yeah, we're still kind of thinking a little bit about why that might be. Maybe there's some model drift things, but maybe we're just not fully capturing internal variability. I think I'm running out of time. Have I got time for just 2 quick slides? Maybe?
Sure.
Sure.
You won't have time for questions.
Okay, just I want to highlight, we're looking at sea ice melt. There's a bunch of models that give us sea ice melt information, so that's cool. They all happen to use size 5.1.2, which is interesting. Quickly, this is what they look like. This is July, averaged over a few years. We include CSM2 large ensemble 2, and then we have observations from this Sentinel-3 melt pond product. We see some very large differences between the models and the observations, and we want to find out why. If you're interested, please get in touch. And then final shout out is that, yeah, I'm doing a lot of work on the side to try and improve the ISAT2 products too. So one of the problems with freeboard is we limit it to 50% concentration. I'm trying to extend that using some kind of fancy interpolation schemes that Will Gregory and others put together to increase that down to open water. Then I'm also working on an all-season thickness estimate from ISAT2, which is showing really good agreement with that Jack Landy's ISAT2 product that Molly just showed, and a bunch of validation data too. And that was just submitted to the Journal of Glaciology with Jack involved in that study. So yeah, lots going on. Excited to see what you all might think of it. Thanks a lot.
All right. Thank you, Alec.
10 seconds for questions. Perfect.
10 seconds. Yeah, Molly, you might want to get in touch with him about whatever products they have too. Also, Alec, you couldn't hear the reaction from the room about the CESM2 less melt, but there might be some words to be had.
Okay.
I think those will be a follow-up later.
Okay, cheating was the wrong word to use there. I'm sorry.
Yeah. But let's go ahead. Our next speaker, actually coincidentally, is Jen, and she is going to talk to us about when snow becomes rain.
Alec, are you still there?
I am, yeah. Good.
Yeah, so basically I just wanted to say, like, what we did for this ESM2 less melt simulations was go back to the pre-industrial control run and adjust some parameters within the observational uncertainty, because we knew that the model ice was too thin, and we knew we could adjust the albedo and that would have preferentially affect the Arctic, where we were seeing that bias even worse. But then I just want to say, like, the reason we're reacting to cheat is because we had no idea what was going to happen, right? You just run the simulations and see what it looks like by the time you get to the observations under the forcing.
Right.
So it's really, it's a model development exercise, and we're all really proud that it came out #1.
Oh yeah. No, yeah, sorry, I was joking. I promise I was joking.
Okay,
I'm mostly impressed.
Okay, yeah, well, are you going to publish that? That's my question.
I'll put it on a website somewhere.
Okay, thank you so much, Alec. Okay, so we're going to shift gears and talk about some work looking at atmospheric processes. So where snow becomes rain in the atmosphere under warming. And this is work that was largely led by now Dr. Thompson Munson, who works in Travelers Insurance now, but the paper that was about this work over Greenland got published this spring, so I thought it might be kind of fun to share with all of you. And then I did make some slides at the end trying to look at these processes across all of the Arctic and CESM2. Oh, there we go. So part 1 is this published paper. You can read it. It's in GRL, an observational constraint for future Greenland rain in a warmer atmosphere. Just GRL, you have the key points, and so I can kind of lean on those to efficiently communicate what we found, which is that the first one is just basically a methods one. Warming alone, applied to spaceborne radar observations, provides a useful constraint on future Greenland rain occurrence. The second are sort of the results. So we have rain could double with 2.3 degrees of near surface warming. So that's a lot more rain over Greenland. And projected 21st century warming makes rain possible at all elevations and in all months. So basically, we're looking at a rainier Greenland. We're starting to see evidence of that from the limited number of ground-based observations that are there. But this observational data set that we're working with is actually a satellite. It's a spaceborne radar that makes measurements over most of the ice sheet. So we can really start to constrain where and when we might start to see more rain. So yeah, here's the strategy. These spaceborne radar observations are from CloudSat. We build up local statistics over time to map and understand the sensitivity of going from snow to rain. And we're very conservative and simple in our analysis approach. We're detecting the precipitation by saying you have to have a radar reflectivity greater than 0 dBz. And we're only looking where CloudSat can make that measurement well, which is not right at the surface because there's strong ground clutter from the surface. So it's at about a kilometer above the ice sheet, which is kind of nice because it helps us differentiate from things like blowing snow. And these are big events. Like if you have a precipitation that's being detected a kilometer up, it's definitely precipitating. And then for the snow to rain threshold, this is kind of a fun atmospheric science fact, right? We always think about phase transitions as happening very abruptly as soon as you get over 0 degrees. And that's sort of true, but actually there's things like evaporative cooling. So anybody who lives here in Colorado probably knows if you're up in the mountains and driving back, you can sometimes see snow even though it's well above 0 degrees, and that's because there's some near surface evaporative cooling. Colorado's very dry. So we went pretty simple here. We used a threshold of 2 degrees Celsius to really try to make sure that if we're saying it's raining, it's definitely raining. So what we can do is just look and see, for one data granule, what this kind of looks like. We get these swaths of radar reflectivity, and we can make a kind of transect across the ice sheet whenever the satellite passed over Greenland, and then we can discriminate between rain and snow. So the present day observations are really consistent with rain being pretty rare, only along the coasts and during summer. So this is figure 1 from the paper, just showing, again, accumulated over 2006 to 2020, this map of where it's snowing and raining in A and B, and then the seasonal cycle of that. We can see exactly what this text said. Rain's pretty rare. midsummer, and along the margins are where we see it. And we can see, we have a lot of data that are going into this, so that's kind of cool. This satellite is no longer operating, but it was designed to last for 3 years, so it did pretty well. And so then once we have this distribution, it sort of serves as a foundation for assessing the potential for future rain increases. And here what we're just doing is we're just taking the observed distribution and saying, where would we change phase based on our simple thresholding? Now, this seems very simple. It is very simple. But just ask folks about modeling precipitation over Greenland. You can ask people here at this meeting, and you'll know why this is a very effective and useful thing to be thinking about. It's hard to model precipitation. Precipitation phase over Greenland has been something that CESM has struggled with. So what we do is just, really simple. We say, okay, if it warms by 1 degree, how much more rain do we get? How about if it warms by 10 degrees? So here's just the fraction of Greenland precipitation consistent with rain under these different warming levels. So in black at the bottom, that's our current day. And then as you move up, obviously more rain. So you can pull out a lot of statistics here, raining a lot more in the summer, but starting to get rain in all months when you get to 2.3 degrees of warming. And then we can make maps. So for example, the fraction of Greenland precipitation consistent with rain under different warming levels. So 2.3 degrees is actually where rain doubles. You can see rain is, still not occurring at the summit of Greenland, but, we're starting to get it along the margins. At 7.3 degrees Celsius of warming, 50% of the precipitation below 1,500 meters is rain. And with 10.7 degrees, rain is 50% of the precipitation. So we did look a little bit at how much warming happens in some of the projections over this next century. And the 2.3 amount of warming is something that occurs in almost all scenarios, under all emission scenarios, under all models. The 7.3 and 10.7 are not really within the scope for the next century. So I think, this is kind of a nice example of how you can start to pair maybe more complicated estimates of how much it's going to warm with these very simple kind of warming level-based estimates. So some more maps, just showing you as a function of the month of the year. Again, you're getting a lot more rain, during the summer and during these kind of shoulder seasons like September and May. That's when the warming really starts to create more rain in the central part of the ice sheet. So the 3 key points, I already said them, so I won't say them again here. You can check out the paper, but it's a nice, I think, example of how you can think about things like how much is it going to warm and how is that going to change precipitation phase without having to really even go through using a model at all. But obviously we have models, so it's kind of fun to use them and think about them and think about what to compare this to. So we started looking at this in CESM2. Before I go to that, though, I just want to advertise that even though CloudSat is no longer in space, EarthCare was launched about a year ago. This is a joint European-Japanese satellite, and it has a spaceborne radar and LiDAR on board, and is making measurements in the polar regions. And I think this is something for those who are polar scientists and interested in observations to constrain things like clouds or boreal fire cloud interactions or things like that. These are satellites that are up in space that would be very attractive tools to use, and so I think you should really keep an eye on these data and use them. Okay, so just briefly, I'll talk a little bit about this, looking at snow to rain in CESM2. I've been trying to take an event-based approach with this, again, so that I can try to use some of the kind of conservative and simple principles of atmospheric science to try to really understand where snow might turn into rain. And so the Large Ensemble Project, and in particular the 6-hourly MORE runs, and anyone who can tell me what MORE means can get a piece of candy from me later. Jonah, do you know? Mother of all runs? Yeah, right. So we can build up these local statistics, and that's kind of cool because looking at the monthly mean when you're looking at precip events is kind of insane. Precip is very intermittent. And if you want to understand the atmospheric structures associated with precipitation phase changes, looking at the monthly mean atmospheric precipitation structure is not the way to go. You need really high frequency information. So I'm being really conservative and simple and thinking about these things. Large precipitation events is what I'm interested in. I really want to see where we went from a large amount of snow to a large amount of rain. And again, being very conservative with some of the snow to rain thresholds. And here just comparing early 21st century with late 21st century and trying to think about where this transition is happening in the atmosphere and what are the processes that control it. So this is just the 275K contour in the bottom level of CESM2 during these large precipitation events. So you can see this contour from May through September when it's up in the high northern latitudes. Other months of the year it's further down, like in Colorado in October. So basically you can start to see, okay, where are we going from like a regime where we could have some snow to a regime where it's just basically all rain. And obviously that moves, as we get into summer, that transition moves towards the pole. And so then I added in dashed lines the late 21st century. So just seeing, this kind of encroachment into the Arctic Ocean of where we can start to have conditions where like the atmosphere is really not going to support the development of snow. It's really going to be rain. One thing I really noticed when I started looking at this was just how much this near-surface air temperature contour in the bottom level of the CESM model, CAM, how much it looked like the ocean and looked at, obviously the near-surface air temperature is very strongly controlled by the ocean underneath it, and the ocean, in this case, is probably a lot of ice-free conditions starting to warm up, but, not getting too warm. But then I was thinking, it's like, that's not always the case for what's controlling the phase of the precipitation in the atmosphere itself, right? So I thought, oh, this would be kind of fun to think about, like, what does it look like a kilometer above the surface? Like, how much is the ocean influencing that? And that's where, yeah, this is these same contours, but now looking about 1,200 meters above the ground surface in the atmosphere. And one thing that's really interesting, to me at least, is just how different these look. So, rain doesn't generate at the surface. Rain generates in the atmosphere in a cloud, probably at a kilometer up. And yet there's a lot of studies, if you read them, they're trying to figure out how snow is turning into rain by thinking about how the surface temperature is changing. And there's a lot of interesting, rich structure in the lower atmosphere about what that vertical profile of temperature looks like. And that's going to be really important for the phase of the precipitation that's actually hitting the surface. So I think that's really cool, and I'm planning on playing with this some more and thinking more about it. Obviously, I didn't do as much playing because derecho was down, but I got some plots of CESM2, and I think I can call it a win. So yeah, I think that's all I had for you all. Just this question about where snow becomes rain with atmospheric warming. I just really encourage you to not forget about the atmosphere, because the atmosphere is actually the place where that phase transition is going to happen. So thanks.
All right. We have anyone? All right. Thank you, Jen. If you have questions, you can come find her after. Our next speaker is online. We have Ash, and they're going to talk to us about how winds are impacting Arctic sea ice. Unfortunately, because of illness, they're not with us in present, but you can go ahead and share your screen when you're ready.
I'm all shared.
All right, we can hear you and see it. Go ahead when you're ready.
All right, awesome. Sorry I'm not able to be here in person today. Maybe tomorrow though. But today I'm going to talk about isolating the contribution of observed winds to recent Arctic warming and sea ice loss. I'd like to thank all of my co-authors and all of the people who have funded me on this project. And I'd also like to say this was recently submitted to the Environmental Research Climate Journal. It's not available yet, but hopefully when it makes through reviews, it will be. All right. So we all know that the Arctic is warming 4 times faster than the rest. And here we can see that the decadal global and Arctic temperature trends from this ensemble show a large 0.6 degree Kelvin decade spread amongst the ensemble members and spread in the Arctic amplification factor of 2. This ensemble does capture the observed Arctic warming and Arctic amplification factor, but knowing that this climate model has so much internal variability adds unreducible uncertainty to our predictions of Arctic climate. So we need to understand the internal variability of the Arctic climate system better. But from previous analyses, we do know that the observed winds are critical to reproducing the observed sea ice and temperature trends and internal variability. Driven from those results, previous studies also asked how much does the wind contribute to recent warming and sea ice loss using historical climate models forced with observed winds. But what our study wants to ask is how much warming and sea ice loss the observed winds alone can generate without anthropogenic forcing and in a pre-industrial climate instead. But one other fact we want to consider is the amount of influence the observed winds has on the sea ice dependent on mean state sea ice thickness. For example, thicker sea ice has more mass and is more resistant to wind stress. Furthermore, if we apply warming to both slabs, the thinner sea ice slab is more affected than the thicker sea ice slab because it has more thermal inertia. So we want to add as a caveat, what is the influence of the observed winds alone on recent Arctic warming and sea ice loss as a function of mean state sea ice thickness? So set up for this experiment, I'm using wind nudging to nudge the model winds to, in this case, reanalysis winds. So I'm using CESM 1 version 2.1. I'm using a fully coupled version, because I want the sea ice to respond. And again, I'm using a pre-industrial climate because we don't want the anthropogenic forcing. And as for nudging, I nudge the horizontal wind components, U and V, with reanalysis every 6 hours from 1950 to 2023 over 60 to 90 north and above 850 kilopascals. So these are all the data sets that I used for observations. Or OBS, I'm using Array5 for reanalysis for temperature and sea ice, GISTEMP for temperature anomalies, and then NSIDC sea ice index for the sea ice. And for the PI control, this is sort of our baseline pre-industrial control, and it's just a random sample of the CESM2 pre-industrial control. And then PI nudge is our pre-industrial sort of climate 3-member ensemble, where each ensemble member has its wind nudged according to the previously discussed methodology. PI nudge less melt is exactly like PI nudge, except it has modifications from KL 2022 to generate thicker mean state sea ice. And then PI nudge more melt is also like PI nudge, but it has modifications for mean state thinner sea ice. Now, PI control and OBS sort of the two ends of the spectrum, and we expect that our nudging experiments are going to fall somewhere between them. Initially, for PI control, if a nudging experiment is sort of within our pre-industrial control, it means that the nudging experiment could have plausibly occurred within the pre-industrial control without forcing from the observed winds. This is just a quick overview of what the mean states look like, particularly looking at the sea ice. On the top, I've got the Arctic sea ice extent, and bottom volume. These are the seasonal cycles. So PI nudge, that's the mean state. It comes from PI control, which is, again, the standard CESM2 pre-industrial control state. PI nudge less melt is, again, from PI less melt, which is the blue line, and it has a larger sea ice extent, particularly in the late summer, and larger sea ice volume year-round. And then PI nudge more melt is from PI more melt in red and has a much smaller sea ice extent in the late summer, and again, a smaller sea ice volume year-round. As to state, PI more melt, sea ice extent and volume are close to modern day sea ice extent and volume. So to start, we looked at the annual Arctic temperature over 1980 to 2023. And for all of these results, we're only looking at this time frame. And for the rest of the line plots, OBS is going to be in black, balance of PI control is going to be in light blue, PI nudge will be in purple, and PI nudge less melt is going to be in blue, and PI nudge more melt is going to be in red. And the closer to the OBS, the nudging ensembles are, the stronger the influence of the winds, and the closer to the PI control baseline, the weaker the influence of the winds. So looking at the three ensemble members from PI nudge, we can see that they do not reproduce the observed warming. We can also see that although PI nudge less melt is cooler and PI nudge more melt is warmer, neither one of them are also reproducing the observed warming. And all nudging experiments explain about 20% of the interannual variability. So the observed winds have some influence over temperature variability, but not long-term trends. And changing the sea ice thickness has no effect on that result beyond changing the mean state. And then we looked at the Arctic temperature annual and monthly trends, temperature trends. And again, none of the, these wind nudge experiments are reproducing the observed or monthly annual trend. Sort of all of these trends are within what we'd expect for a pre-industrial control. For example, all the nudged experiments are between like 0.11 to 0.14 Kelvin per decade annually, whereas compared to the observations, that's about 0.7. And all experiments reproduce similar trends regardless of mean state. The sea ice thickness is not affecting the contribution of the observed winds to temperature trends. However, all of the experiments reproduce the seasonal pattern of the observed warming trends, i.e. we get the strongest warming in the fall, spring and fall, and the weakest in the summer. Moreover, so in total, the experiments are explaining about 16 to 20% annually, and they explain the most warming in the spring, about 30-40% in April and May. We also looked at sea ice, looking at September sea ice in particular. Again, none of our wind nudge experiments reproduce the observed trend. They do explain about 12 to 8% of the interannual variability. And again, changing the sea ice thickness mean state is only, again, affecting the mean state. It's not affecting the trend. And then if we were to back out and look at sea ice extent trends more broadly, we can see that, again, the wind nudge experiments are not reproducing the magnitude of any of the observed monthly or annual trends. And in total, in September, the sea ice, the wind nudge experiments are explaining about 10 to 16% in September and like 1 to 8% in March. We are reproducing roughly the seasonal pattern of sea ice loss trends. So we're sort of explaining some of the seasonal variability, but again, we also note that the sea ice, all of the wind nudging experiments produce roughly the same trends. So our mean state is again not affecting the wind contribution. We also looked at local temperature and sea ice trends for each season. For running this plot, I'm going to outline the format here. So each column is a season. The row on the top is going to be the observations ERA 5. The bottom row is going to be PI nudge. So that is going to be the pattern correlation between PI nudge and the OBS and ERA 5. And any stippling would indicate that the trend is outside what we'd expect for a pre-industrial control. So if you look here, for the Arctic temperature trends for every season, you can see that PI nudge is not reproducing the magnitude or spatial extent of trends, of warming trends in any season. It does have roughly the same spatial pattern of trends as the observations, supported by some fairly high pattern correlations. I'd also like to note that PI nudge and the observations have their strongest warming trends in the same location, and this is true for every season. And I'd also like to note that there's no stippling on PI nudge for any season, meaning that all trends are what we would expect to see for a pre-industrial control. If I were to focus in, On DGF briefly here, we have this pattern of warm Arctic, cold Eurasia. We do see this pattern in observations, but some of the research is still divided on whether this is forced or internally driven. Given that our wind nudge experiment is reproducing this pattern, we suggest that this pattern is internally driven. And I'd just like to quickly note here that, so on the top is PI nudge less melt, and the bottom is PI nudge more melt trends. Both PI nudge less melt and more melt are nearly identical to PI nudge, so both increasing or decreasing the sea ice thickness doesn't matter. It's not having any effect on the wind contribution to temperature trends. And lastly, here's the Arctic sea ice trends for every season. Again, PI nudge is not reproducing the magnitude and spatial extent of the sea ice trends in any season. PI nudge does have approximately the same spatial pattern of trends as the observations, but it's generally performing worse for sea ice than for temperature. And PI nudge and observations do have their strongest sea ice loss trends in the same location for at least JJA, SON, and DJF, but not for March, April, May. As you can see in the Barents Sea, we have a lot of sea ice loss in the observations, but almost nothing in PI nudge. Some additional sort of discrepancies include the Sea of Okhotsk for March, April, May, and the Bering Sea for both March, April, May, and DJF. We do see some stippling, but for all the trends, it's about smaller than 2% per decade, so we can sort of disregard that significance. Again, I have here's the PI nudge less melt is on the top row and PI nudge more melt on the bottom row. Again, very, very similar results to PI nudge for the sea ice trends. So again, no effect on sea ice trends from changing the sea ice thickness. So in conclusion, the observed winds fail to reproduce the magnitude of recent Arctic warming and sea ice loss. They can partially reproduce the interannual, seasonal, and spatial variability of Arctic temperature and sea ice. So in short, like observed winds drive some of the Arctic variability, but not long-term trends. And our results are independent of mean state sea ice thickness. I do want to mention that we had to diagnose and remove wind nudging induced mild drift. If anyone wants to learn more about that, I'd be happy to chat about it. Thanks for listening, and I'll take any questions.
Thank you, Ash. We have time for a question or two. All right. We don't have any questions in the room. Thank you so much, Ash, and hopefully you can rest your voice, and maybe we'll see you tomorrow.
Great.
Our next speaker is Ling Wei, and she's going to talk to us about microplastics and sea ice.
Thank you very much. I'm Ling Wei from CU Boulder. And today, I'm really excited to get to share more about work I have done simulating microplastics in the Arctic using CESM2. So before I continue, I would like to take a moment to thank my mentor, Alex, and our collaborator, David Bailey, for their valuable input and support. So we may hear a lot about microplastics lately and how pervasive they are in our daily lives. This leads us to wonder what actually happened to plastic after we threw it away. It never really disappears. It just gets smaller and smaller until it becomes invisible to our naked eyes. So we call these small fragments as microplastics. By definition, microplastics are just small plastic particles with mean diameter smaller than 5 millimeter. And because of rapid increase in plastic use over the past decades and the mismanagement of waste, microplastics are now prevalent in the global environment and are a massive marine problem in the global oceans. And aside from the obvious pollution, the integration of microplastics poses questions about their effect on our Earth's climate system and health risk to consumers across food webs. And one of interesting question is if there are any microplastics in the Arctic. Unfortunately, because although the Arctic is far away from the direct source of anthropogenic pollution, recent studies have shown that microplastics can be found almost everywhere in the Arctic. The rivers, oceans, glaciers, sea ice. So the microplastics were first discovered about roughly 10 years ago in the Arctic in 4 ice cores retrieved from different locations in the Arctic Ocean. And in this initial study, a total of 6 synthetic polymers were reported and its concentrations were estimated. Surprisingly, the concentrations of microplastics are really high, and it's even higher in the Arctic sea ice than the underlying ocean. So this high concentration in the sea ice later has been confirmed using more samples collected at different locations and in different years. So here, this schematic plot summarizes the typical range of microplastics in the Arctic sea ice and ocean, and we could see that the concentrations of microplastics are about 1 to 6 order of magnitude higher in the sea ice than in the underlying ocean. So that means the microplastics have accumulated far from population centers, and Arctic sea ice is an important sink and means of transport for microplastics. But how do they get there? We do not know. Well, the reasons for its high concentrations in the Arctic sea ice are still a mystery, and with this high concentration, the distributions of microplastics in the sea ice and ocean are still underreported. And additionally, few modeling studies even have focused on the Arctic marine microplastic problem and explored how big the impact of Arctic microplastic in sea ice on global oceans. That being said, how the ice growth and melt processes affect microplastics in sea ice and ocean are largely unknown. So to better understand mechanisms and factors concentrating microplastics in the sea ice, we have been working to implement microplastics as a new class of passage tracers in the CSM2. So far, we have added 2 tracers. One is neutrally buoyant and one is positively buoyant microplastics. Both tracers are added in the sea ice and ocean component of CSM2 plus the coupler, and we applied a constant rising velocity to the positively buoyant microplastics, so buoyancy only affects the tracer movement in the ocean. And we are not modeling the negative buoyant microplastics in the model because it is just that the negative buoyant microplastics will not reach to the Arctic Ocean where they will interact with the sea ice. Well, because we would also like to know how microplastics get trapped in the sea ice and released from the sea ice. There is ice melt processes. Fundamentally, we need to know how to parameterize them in the model. There are 3 factors that we could really play around. The optic factors for the congelation ice and fragile ice growth, and the release factor for microplastic, there is top ice melt process. Currently, the observations have typical no knowledge of ice history to really understand how observed concentrations relate to these parameters. So to address this, we are collaborating with the lab team from University of Washington who grow ice artificially in the tank with microplastics to investigate these parameters. So we will decide on these final parameters in the near future based on our sensitivity tests and lab results. But here we just assume the same amount of microplastic concentrations in the sea ice as in the ocean. There is an uptick factor for the uptick factors. So once the model is set up, we have run 3 1-degree sea ice ocean coupled simulations with microplastics. The first simulation only includes uptick factors where microplastic will be trapped into the sea ice during the ice growth process. And the second one does not have neither uptick nor release factor. And the third one, the third simulation includes both uptick and release factors, where microplastic will get trapped into the sea ice and released from the sea ice. So the model the model is forced by a global microplastic forcing field, which prescribes the mismanagement plastic waste input along the coastal lines in proportion to the total population along the coastal line. So we scaled down the total plastic input for neutrally buoyant microplastics and positively buoyant microplastic by a factor based on the global demand for each type. So 19% for neutrally buoyant microplastic and 49% for the positively microplastics. After running for 60 years, we now compare to the ocean surface total microplastics of simulation 1 and observations. And it shows good agreement with observations and can change some key features in the model. For example, the Pacific garbage patch. And then we wonder how ocean microplastics change globally by having microplastics in the sea ice. And here I'm showing the difference maps between the cases with and without uptick factors. The top panel is showing the top layer difference maps, and the bottom is showing the vertical integral of microplastics for neutrally buoyant and positively buoyant microplastics. Both figures show less microplastics in the Arctic region and more microplastics in the North Pacific and North Pacific jars. Although the changes in the North Pacific is quite small, about 1% of total plastic change. But that indicates that means that the uptick factors could really reduce microplastics in the Arctic Ocean and increase microplastics in the North Atlantic and North Pacific regions. Now let's switch gear and see what happens in the Arctic. Here I'm showing the ocean surface microplastic concentrations and microplastic concentration in the ice in year 60 of simulation 1. And we can see two things. The first, there are some differences in the spatial maps for neutrally buoyant and positively buoyant microplastics in the Arctic Ocean. And secondly, the model can really reproduce higher microplastics concentrations in the sea ice than in the ocean, which is quite consistent with observations. But note that this simulation only includes uptick factors trapping microplastics into sea ice during ice growth. And we want to know if there are any effect for the release factor. So simulation 3, which includes both uptick and release factors, where microplastic will be taken into sea ice during ice growth and released from sea ice during the ice melt. So here, let's start with neutrally buoyant microplastic first. So here I'm showing the comparison between the cases without and with release factor. And the left panel is showing the concentration in the ocean, and left panel is showing the concentration in the ice. And well, we can see the ocean concentrations of microplastic in both cases are very similar, so meaning that there are very small differences between these two cases. And also we can see we still have much higher concentrations in the sea ice than the underlying oceans. So this is also true for the positively buoyant microplastics. So to summarize, the model can really reproduce higher microplastic concentrations in the sea ice than in the ocean, which is consistent with observations. And the model shows differences in spatial patterns for neutrally buoyant and positively buoyant microplastics. And the upticks of microplastics in the sea ice does affect Arctic and North Atlantic microplastic concentrations. And as for next step, I would continue to work exploring how microplastics are exchanged between sea ice and ocean, and assess the role that sea ice plays for changing the Arctic microplastic distributions. And if possible, I would further investigate how future climate will change the impact of microplastic distributions in the Arctic. So I will stop here, and I'm happy to take any questions. Thank you very much.
Thank you, Ling Wei. Do we have any questions?
So could you go back to page 10, please? Yes. Could you give some more explain about why there are regions of the microplastics increasing? I understand that if the sea ice uptakes the plastics, it reduces, but I don't understand why it increases.
Well, to be honest, I do not know either. Because and also, I will take into deeper depths about why it increased in the North Atlantic and North Pacific if we don't really have uptick factors in the model. But so far, I don't really have a confirmed clear answer to you, like why we have really increased in the North Atlantic. But that's really a nice question, and I'm looking forward to it. Yeah.
Are there any other questions in the room? All right, I had a question real quick. If you go forward, I think 2, other way. No, go towards the end of the presentation. Keep going, and go forward one more. So go back. All right, for this one, I thought it was interesting for the sea ice, the positively buoyant microplastics.
Yeah.
On the far right in the sea ice, it looks like there is a big difference if you have the release, whereas you said with the neutrally buoyant it wasn't.
Yeah.
Do you have any idea why those?
So for the release factor, we set is as 0.03, which is same as the black carbon because they are both hydrophobic. But I don't really have chance to why it reduced this much in the sea ice. But also I'm showing the annual mean, so I need to look more about seasonal changes in the microplastics in the sea ice. So sorry, I don't really have clear answer to you as well.
That's all right. Thank you so much. All right. So our last but not least presenter is Dave, and he's going to talk to us a little bit more about CESM 3 and where it is right now.
So I'm also going to go through some of where we're at with the physics as well, because some of you weren't at the winter meeting. So Dave Lawrence had highlighted, some of the processes and things and biases and things like that, and I'm going to go into a little bit more depth about some of these biases that we have in the model. But main thing I wanted to go over first was the sort of timeline that we were looking at last year. So you can see here the timing of the winter working group last year in February, and then the summer meeting last year. We had this ambitious timeline of getting all this physics in that we really wanted in the sea ice. But things change, deadlines shift, and so this is now this year's plan. You can see here I've changed the x-axis, so we're here now, summer 2025. We've done pretty well. We've gotten 3 of these major parameterizations into the model and running in all of our standard coupled simulations. Although the advanced snow physics, we didn't bring in all the aspects of this. I'd be happy to go over it with some of you. So the pond improvements, the advanced snow physics, and then this new congelation formulation. But the thing we're still a little bit struggling with is the flow size distribution wave interaction part. I mean, the code's there. We're just trying to decide some sort of aspects of it that we want to try to overcome before we sort of officially start running with it. All of these other things have been moved probably, again, several times. They keep shifting right on this timeline, and, they're going to be hopefully in future versions. And then another key thing about this is that for the CSM3, we've also developed this new diagnostic package, CUPID. So the acronym is CSM, Unified Post-Processing and Diagnostics. And then as a part of this, I have a new CI's key metrics notebook with a lot of new diagnostic plots and things like that. One of the key additions is that we've added the CSM1 large ensemble and the CSM2 large ensemble onto a lot of the plots. So that helps us put things into perspective with the 2 previous large ensembles and sort of how we're performing in terms of those. We have several spatial plots, to compare 2 runs and things like that. And I'll use some of that in the coming slides. And then another thing that's come up, which is kind of a side rabbit hole thing, is that we're looking at the observational products and bringing them into the diagnostic package. And Dave Schneider's in the room here too. So he's done a lot of this too previously. But what you can see here is the dashed lines are extent. And they agree pretty well generally between all of the different products. So there's the NSIDC official area that you get, and extent. There's this newer climate data record developed by NOAA and NASA. And then there's this European product, the OCSAF, and don't ask me what that acronym is. But anyway, but you can see here that, again, the extent generally is similar in both hemispheres at the sort of min and max periods and so forth. But with the area, they're significantly different. And there's really big differences in terms of how the area is determined in the interior of the pack. And in fact, to the point that it seems like some of these trends might be slightly different too. So it has raised some concerns about what we should be comparing to exactly. I think we've kind of decided that the upper end of this is this NOAA CDR product, and that's probably what we're going to be using as our benchmark from now on. So Dave mentioned the Labrador Sea keeps freezing over. I thought it was worth going into some of the things leading up to this. This is a coupled model problem. And so I wanted to sort of take you through that, what's going on. So we have a high latitude precipitation bias. And we know this, in almost all of our runs, we're just getting too much precipitation, especially over Greenland, but over some of the ice sheet areas in the Canadian Arctic as well. So this leads to enhanced runoff. This is me running off. Anyway, but nonetheless, we get enhanced runoff from Greenland, and then that is we have this funny thing where we fan out both the ice and the liquid runoff using this mapping like this, and we're actually kind of fanning it out a little bit too far over the central lab sea. So we're getting too much fresh water pushed out over the lab sea. And then this is my little approximation of the horizontal mixing scheme. But basically, there's a lot of excessive horizontal mixing going on here too. So you're mixing in fresh water from the boundaries of the Labrador Sea, and you're bringing, again, too much fresh water into the central lab sea. Throw in a little bit of chaos. And so basically, the the fact is that, these conditions lead up to a lot of fresh water, cold water in the central lab sea, but it's not necessarily enough by itself to guarantee that it's going to freeze over. Sometimes, we'll start 3 equivalent runs and all we'll do is just make a small perturbation and one of them won't freeze over and the other ones will. So it's a really challenging thing to really get at. But then, this is kind of low resolution. But it gives you the idea that when it goes, it really goes, and it impacts the meridional overturning circulation, and it just really changes the state of the model. And it's almost impossible to come back from this state. So even if you run out 100 more years, you can't really come back from it. So what have we done to maybe try to alleviate that? We've sort of gone to each of these sources. So reduce the precipitation somehow, by changing the latent heat flux over the ocean, maybe making topographic changes to reduce the precipitation over Greenland in particular, reducing the flux locally using sort of artificial methods like restoring or just, reduction factors or something like that. And then also changing lateral and vertical mixing parameterization, sometimes locally in the lab sea, sometimes globally. So those are the routes that we're taking, and there's been some promising results with some of these. The other interesting thing, back to the sort of OBS and then sort of model, is that we noticed that the Antarctic sea ice extent has been expanding very much. And, when you looked at the seasonal cycle and sort of, in sort of a CSM2-ish configuration, the seasonal cycle was actually really good and it compared very well to the OBS. But what you'll notice here is that there's this interesting pattern of the sea ice being too high compared to OBS at the ice edge, like around 90 and minus 90, and yet it's too low here at 0 and 180. And so it's like somebody just grabbed it by the sides and pulled on it, and suddenly you actually get about the right overall seasonality, but there's still significant regional biases. And then somewhere in the development of the MOM simulation and the vertical coordinate, we noticed this got a little worse here. And then when we changed to the vertical HICOM coordinate in the most recent simulations, now you'll see the bias is just high all the way around. So we have a really high Antarctic sea ice bias. So that's a spatial picture. This is just to give you this idea of what I said earlier, that the 2 techniques for retrieving the ice area can still give you very significant pictures of, or picture differences of the ice area interior in the pack. So I'm kind of getting there. So anyway, so here's the seasonal cycle that I was talking about, and this blue curve here is one of the control runs that we have from pretty recently, and you can see it significantly overestimates the area in the winter months in the southern hemisphere. And then here's the 2 observed products that I talked about, the CDR and then NSIDC. Interestingly, CSM1 looks really good compared to CDR. CSM2 looks really good compared to the NSIDC, so you can pick whichever one you want. But one of the sensitivity runs, well, we did several. We did a nudge wind run. Ash talked about this. It does help a little bit. It moves the wind stress maximum a little bit towards the pole, but it doesn't really resolve the overall extent that well. But what's very interesting is this new run where we use the GFDL PBL. You see that it's not only much closer to the old runs, it actually is getting the seasonality better too. So it's really surprising. Now, is this a candidate for CSM3? We don't really know at this point. We're continuing things. We still have the wave interaction runs. We hope to maybe get that in. It does also decrease the ice extent somewhat, but it's not really going to fix the overall thing. And then a very hot off the press thing this morning that I did just from derecho coming back up. You can see here that I did this run where I changed the mesoscale mixing parameterization, the Gent-McWilliams, slightly. And you can see it does reduce the overall sea ice extent in the southern hemisphere a lot. Doesn't quite change the seasonality like we would like. But anyway, these are all potential candidates. And I got a minute left, but this is just basically summarizing everything I've said. But I think the important thing to think here is we keep harping on the CSM administration to say, you know, the southern hemisphere is important, and we don't want to live with this bias. So with that, I'll take questions.
All right. Thank you, Dave. So yeah, if you were here in the winter working group meeting, you might think you're still having the same problems, but we really have been looking into it and trying to understand it. So are there any questions for Dave or even me or the other co-chairs or anything like that? I'm going to start with Alex.
Yeah, thanks, Dave. When did you look at the rest of the Arctic? So outside the lab sea, how does the sea ice look beside the lab sea, like thickness-wise?
Yeah, I didn't really show the results here. It just varies between the runs, but overall, our overall Arctic bias is pretty good in general. It looks pretty reasonable. So, but that's another thing we still have to worry about is we could still potentially have to tune the Arctic sea ice a little bit. So, but yeah, right now we're focused on lab sea and Southern Ocean. So, yeah.
Yeah, thank you for the presentation. So, regarding this Labrador Sea, so we know that over Greenland, over the Canadian Arctic, there is a snow cap. So whatever, when you get 10 meters, then you're gonna just send all like frozen runoff. Have you tried, if your snowpack is uninitialized, the moment it's building, it still freezes over?
Yeah, we did. I didn't mention those experiments, but basically all it does is just delay it, you know, because it takes a while. It finally builds up to the 10 meters, and then you start dumping the ice runoff and the snow or the liquid runoff in, and it freezes over. So we had one run, went 240 years, and then the lab sea froze over. So, yeah. Exactly. Yeah. Yeah. Ed?
Great talk, Dave. This is maybe more of a comment or like a PSA, but if you go back, I think, to your slides where you're showing all the sea ice area extent time series, where you were validating from the observation estimates. And I bring this up because it came up in actually a review I made very recently. If you look at the NSIDC area in the top left there, or in the top right? Like if you look at the red time series, the first decade or two, it looks like it's increasing. And the issue, I'm fairly sure, is that they have different sized pole holes.
Yes.
And the NSIDC website, they just give you the raw number, and you have to kind of dig in to see, oh, there's just a bigger pole hole. So you're actually summing over a smaller kind of mask early on, and it's basically an artifact. Yeah. And I think OSISAF just assumes that the pole hole's covered in sea ice.
Yeah,
right?
Absolutely. And and that's why generally NSIDC sort of sticks to extent, because they do fill in the pole hole with extent, but they do not for area. And so, yeah, you're right. There are some weird artifacts there, but, you know.
Not for the NSIDC area time series.
Right.
But I just want to point out, because if you just...
This is the official NSIDC index. But you're not filling the pole. I am not.
Yeah, and that's the issue, that if you go on the NSIDC website and you just download the sea ice area index, this is it.
Yeah.
And you have to, like, I mean, and this happened, I was reviewing a paper and this came up, and then it matches the others, doesn't it?
Yeah.
But in terms of the mean state, I think, but in terms of the trends, it matches the others a lot better.
Yeah. I mean, it's right. Yeah. Right. So maybe it's a rabbit hole, but nonetheless, it's just worth highlighting these big differences and sort of what our truth is. That's all I was trying to say. So yeah.
Okay. Maybe the big takeaway is that when you're using these observations, be really careful and read the documentation about what you're actually using.
Yeah. Yeah.
Because there are some gotchas in there, and we've run into them in this. Are there any other questions, comments? All right, well, I think we're almost done. I want to make one announcement, which is if you're on the Polar Climate Working Group email list, Ed and Hansi and I will probably be emailing you about using resources. If you have a resource allocation, if you don't, you can ask for resources from us. There's some changes to the way, what CESM 3 might do and how resources will be allocated. So we might have opportunities for contributing to different sorts of community experiments. So we'll probably seek feedback for that. But otherwise, we'll send out emails and we'll have a winter working group meeting. But thank you for coming. We have a break, and then it's the afternoon session to celebrate the history of CESM 3, and there will be the chief scientist there, so our very own Marika will be on the chief scientist roundtable discussion thing. Thank you.